Good evening, everyone. It gives me immense pleasure to welcome you all to the day for our FDP on advanced trends in renewable energy systems and smart power technologies. Over the past 3 days, we have insightful sessions and engaging discussions that have enriched our knowledge and inspired new ideas. As we begin today's session, I encourage everyone to actively participate, interact with our speakers, and make most of the today's learning opportunities. On behalf of the Triple department, I extend a warm welcome to all of you and wish you a productive and enlightening day ahead. Thank you. We can start our first session. It is my great privilege to introduce our distinguished speaker for this session, Dr. Vinita Chellapan, Professor in the Department of Electrical and Electronics Engineering at Government Engineering College, Palakkad. She has more than 25 years of teaching experience and over 2 years of industrial and research experience. She has previously served at Government Engineering College, Kannur, GEC Kozhikode, and GEC Trivandrum. She also worked as an engineering officer at the Central Power Research Institute, Trivandrum. Her research interests include optimal and nonlinear control, spectral numerical method, control of power electronic systems, and guidance and control. With her rich academic and research experience, we are indeed fortunate to have her with us today. I request all the participants to extend a warm welcome to Dr. Vinita Chellapan and look forward to an enlightening and inspiring session. Thank you, ma'am, for joining us.
Thank you. Am I audible? Thank you, Archana. Hello,
yes, ma'am,
am I
audible.
audible? Yes, thank you. First of all, I would like to thank the organizers, Professor Sharanya P. and Professor Archana P. of Sribati Institute of Technology for inviting me for this FDP on advanced trends in renewable energy systems and smart power technologies. Thank you. So shall I share my screen? So is the screen visible?
Yes, ma'am.
Thank you. Today we have, I think this is the fourth day of your FDP. And most of you might have got a lot of information regarding different research trends in renewable energy systems and smart power technologies. So today my talk is on a little different directions, which includes the electrical control of electric drives for electric vehicles. And I will start from the industrial drives to intelligent EV propulsion system and go into different control aspects. Okay. So these are the directions of my talk that I'll be giving today. So I'll start with the electric drives and go on into its evolution, as well as go on to the modern electric drives in industrial applications that are there. Then I will directly transit to the electric vehicles. Then after that, I will start the control perspective of the different control perspectives that are mainly the PID control, the nonlinear sliding mode control, and if time permits, a little bit on the sensor operation of drives. Okay, so this is the direction of my talk. So let me start with the introduction to electric drives. Okay, so we all know that there are electric motors everywhere. Wherever we look in our houses also, when we use an electric vehicle, we have a motor in it. In our kitchen, there is a motor. So wherever, if we look around, we can see a motor, because now I'm sitting in front of a fan. So there is a motor involved in it. So electric motors are in fact everywhere. So the major concern, then what is an electric drive? So today we will be discussing on electric drives rather than electric motors. So let us see like how different motors are being controlled for various applications for an industrial setup. So if we have in the industrial drives technology, so let us see why do we need an electric drive. Before going into what is an electric drive, let us see what are the different applications of electric drive. So how is it different from a motor? So we have electric industrial drives in various applications. For example, in the case of a conveyor belt, where we need a constant speed as well as a constant torque. And in the case of an industrial robot, we can see that the precision is one of the major concerns in the case of an industrial robot. And so it should have a millimeter accuracy for this industrial robots. And if we have an elevator has a 4-quadrant operation. And in the case of an elevator, we can also have a regenerative braking for the elevator. And also there should be comfort. When we use a drive inside in an elevator, there should be comfort for the passengers who are getting in and out of the elevators. Then we have the CNC machines, which is extremely used by used for a lot of applications. So we require to have a synchronized operation in the multi-axis, so as to position the spindle and the feed drives. So these are the requirements, mainly the requirements, some of the requirements in the industrial drives sector. And if you move on to the e-mobility or the EV drives, we have the e-scooters and the small vehicles, and also the electric cars. So we, in the case of EVs, when we move on to the EVs, in our electrical transportation system, for example, the drones, we have BLDC motors connected in all the 4 axes. So we can, they are independently controlled, and even if I want to keep it in a trim condition, it is possible by using advanced control techniques. Okay, so these are the applications of drives in the industrial sector. And the question is, why do we want to study this? So in the previous thing, we saw that in a conveyor belt, what is maintained constant is a constant speed has to be maintained. And robot arm, it was a precision positioning, and elevator, it was a smooth comfort. So drone needs to be is very unstable usually, and so it has to adjust to the rapid changes in the system. And all these things are required in the case of an electric drive. So a simple motor connected directly to a power supply cannot do this drive requirement. That is why we require this diverse requirement. That is why we require an electric drive. So what is an electric drive? So an electric drive is something which converts electrical energy into a controlled mechanism, a mechanical motion. So we have a motor which is being controlled. So this is the whole structure, the basic block diagram of an electric drive system. So we can have the power source. In the case of an electric drive used in industries, we can directly connect the grid from the system. But whereas in the case of EVs, we should have the batteries. We should get the power from the batteries. Then we have the power modulator, which converts, like if it is an AC here and the motor is a DC motor, the conversion would effectively be a rectified output. So the power modulator is something which acts based on the requirements set by the motor. And what is the mechanical load? Mechanical load is something that we saw here. For example, in the case of industrial drive, we have the conveyor belts here. These are the mechanical loads which act on these motors. So based on this is actually the mechanical load as well as the power source in fact is set. And all the other things is something which we can change accordingly. So this is the inner picture of a controlled drive system. So this is the basic block diagram of a control system, and one of the most important part is the sensor unit. So which senses in fact the currents or the speeds. For if we sense the speed, we may want to control the speed of the motor, or we may want to control the torque requirement. If I have a varying load, I want to have adjust to the varying load and run the motor at a particular constant speed. So these are some of the requirement, and this is effectively done using a control unit, which we will be discussing, and about what are the different control units available in industries as well as EVs. Okay. So this is in the case of an electric drive setup. This is something we can see. It is a very coordinated system in which power electronics, control algorithms, sensors, and motors work together to achieve a desired motion. Okay, so now let us go into the evolution of electric drives. Okay, so if you go into the evolution of electric drives, what we can see is the first one is the mechanical era, where we had the speeds. The speed was controlled using gears, belts, or pulleys. And we know whenever we think about the mechanical era, we speak about the gear mechanisms, right? So when we think about that, so we we extremely know that they require frequent maintenance and can be dangerous. They can be bulky, and also there can be losses in the system. So then came the DC motor era, where we were able to control the speed using stator armature current, as well as armature voltage, as well as the field flux variations. So here we had a linear control system, but there was a high wear and tear in the system, which was in fact not very effective. So then came the era, which is the AC variable speed systems, where from the 1960s to the 1980s, where we had the power electronics also coming into place. So we were able to control the motors using solid state inverters or converters. So that was one of the revolutions that had happened. That was one of the industrial revolutions that had happened during this period. So in the case of an induction motor, we used to have the scalar V by F control during those periods. But even though it was the induction motors work perfectly well in a lot of industrial applications, and they are very rugged, the dynamic performance of the motors using the V by F control is kind of very low or very weak. Okay, so then came the vector control era, where in the case of a DC motor, we know that the control of the DC motor is kind of easier. So the vector control era, the idea was to bring in a dynamic performance, improve the dynamic performance of the system comparable to that of the DC motors. Okay, so we had the field oriented control, which is in fact an advanced motor control strategy, which converts or transforms the complex rotating three-phase AC currents into independent stationary DC components, which is along the direct axis as well as the quadrature axis. So this decoupling gave the performance of the DC motor capabilities. That was the vector control era. We also had the direct torque control during this period. And then we had the digital intelligent converters, drives, where in fact we also had high-speed DSPs, FPGAs working into the control system. So it improved the performance of all the systems. Then finally, we have the electric vehicle era, which where we have all the industrial motors, all the controls that we have used for the industrial motors were directly applicable for electric vehicles. And also we started from the mechanical era. If you look into the electric vehicle, we can see that from the gear system, we have moved on to a no gear system. So why is it so? In the case of IC engines, we know that there is that means the IC engines for low RPMs, it produces very little torque. But in the case of EV motors, what happens is that it almost 100% maximum torque is available for the different motors that through the control of these different motors. Okay, so and if we want to increase the speed of the system, what can be done? There are it can go into the field weakening area, and we can use the FOC control techniques to change the direct axis current in the negative direction and work on the system. Okay, so this is the evolution of the electric drives. So now now we have moved into the from the fixed speed motors, we have moved into a variable speed electric drives rather than the fixed speed motors. See, all these motors have different load types, and based on the different load types, we can have a different load profiles for the system. Okay, so now in the case of earlier motors, we know that they were directly operated from the AC supply, and the speed was almost fixed. So, and there were no major issues. There were major issues like energy wastage, poor process control, mechanical wear and tear, and high starting current. But now, due to the advancement of power electronics, we are able to select or control and optimize an electric drive, and this can be optimized based on the load profiles that are available available in the industrial sector as well as the EV sector. So we should understand what is the torque speed relation as well as a power relation of the whole system, so as to select a motor or understand how we can control the motor. So the different load profiles are we can have a constant torque load.
Ma'am, Vinita ma'am,
Vinita ma'am.
audio mute ആയി.
Okay, കേൾക്കാമോ?
ഇപ്പൊ ഓക്കെ ആണ് മാം. ഇപ്പൊ കറക്റ്റ്.
Vinita ma'am.
Is it okay? Hello.
ഇപ്പൊ കേൾക്കാം.
Okay. കുറെ നേരമായോ മ്യൂട്ട് ആയിട്ട്?
ഇല്ല മാം.
Okay. So these are the constant torque dynamics based on the different load profiles. That is a constant torque load as well as a constant where that load torque is proportional to omega m square. Here we may have to go for energy optimization algorithms. If you look here, when the speed reduces by 2, we can see that the power reduces by 1/8. So these optimization algorithms can minimize stator copper loss and copper and core losses. And we also have constant power cases where the load torque is inversely proportional to the speed. And here in this we have when the motor goes when the machine goes beyond the base speed, what happens is that the direct axis magnetizing current is reduced so that it can avoid the inverter voltage saturation, so as to and thereby maintaining the motor's higher operational speed. So this is a field weakening region control loop that is mainly used in drives. So based on these load applications, we have to decide what control we have to keep. So we have to set in the load profile of the system before working with the system. And then these are some of the control techniques that are that we all know. One is the scalar control, which is open loop control, which is the V by F control, which we generally use for induction motors. Then we have the closed loop control, which is vector control, and the direct torque control. Okay, so these control techniques, the development of the vector control techniques have been superior compared to the scalar control or the V by F control that was used for a long time. And modern EVs from manufacturers such as Tesla, BMW, Hyundai, etc., they employ the field-oriented control, closely related, that is, or closely related vector control techniques based on the superior dynamic performance. Okay, so we will see that in the coming slides. And we also have direct torque control, where when FOC has an excellent performance requirement, the researchers wanted to have faster methods. That means faster performance for the drives. So they went for a direct torque control where they didn't have to get the information about the currents or do transformations as in the case of a field oriented control. So that is the direct torque control, where we directly get the information, or the torque and the flux is directly estimated, and this has increased the response of the system, and it also didn't have any inner current loop. So that was one of the advantages of the direct torque control. And let us just go into skim through this V by F control. In the case of a V by F control, we can see that if you go for a voltage control alone, the torque is directly proportional to V1 squared, and we can see that V1 squared for a particular speed, this maximum torque is almost constant, and the control here, what happens is only for a low range of speeds. Okay, so because the torque is directly proportional to V1 squared, and we get only a small range of speed control. When we go for a frequency control of induction motor, what happens is that we can see that as the frequency increases beyond a particular period, particular value, we can see that the torque starts reducing because of the saturation. Okay, so now we can just have a look at the V by F control. So if you look into these two pictures together, we can see that during the linear region, if you go for a V by F control, that means V by F control is, if you look into this equation, V1 by F keeps the flux constant. So V1 by F is directly keeps the flux constant, so that I can directly equate this. Torque becomes directly proportional to the flux. So the torque remains constant for the linear range of during the linear range, and beyond the linear range, we have the voltage saturation. So we have the field weakening point here, and during the field weakening, what happens? The frequency reduces here, right? So frequency increases, and we can see that the torque also reduces here. So these torque control, V by F torque control, even if it was easier to control the system, they cannot independently regulate the torque. And so they wanted to have a fast, if they wanted to have a fast acceleration in an electric vehicle, what should they do? So they went for they thought about different systems, and we have the field oriented control. The idea of I hope you are able to see this. The idea of the field control system is that we have the current measurements, that is the rotating IAIB IC, and it is converted into I alpha and I beta. I alpha and I beta, and from I alpha and I beta, if I want to have that means in the field oriented control, what I want to do is I want to have independent controls of the flux as well as the torque. So I want to have two axes or quadrature axis, and I want to have an independent control. So I can have a quadrature axis where the D axis is directly aligns with the rotor flux axis, and the Q axis aligns with the torque. So due to this conversion, the researchers were in fact able to control the torque and the flux independently. So this is the basic logic of the field oriented control. But here I want to, like, if I convert the three-phase AC currents to a two-phase currents, but what happens here is that if I want to get the angle at which the rotor flux axis aligns with the particular in a particular direction, I should get a theta information. So that is in fact estimated in the case of a field oriented control. So this is the basic block diagram of a field oriented control. We have the induction motor, we take the currents, we convert it into the alpha beta frame, using the Clark transformation. And now using the position information, I can theta or triangle, I can get the conversion from alpha beta to PQ free, and that is using this path transformation. And now I have a quadrature axis control as well as a direct axis control. So this is independent because they are at 90 degrees. So that is why it is said to be independent control. So we have a flux control as well as a torque control. And in the outer loop, if you see, we have the velocity controller or the speed controller. This velocity controller or the speed controller generates the reference currents for the whole system. Okay, reference currents for the whole system, and then we can control the motor using the three-phase inverter. So this is the basic idea of a field-oriented control. So this field-oriented control became very popular because it had an independent control of the flux and the torque. So because of this, it had excellent performance in aligned with that of a DC motor. Now, if we go on to the direct direct torque control, here we are not we are not using the Clark and the path transformations. We are directly estimating the flux and the torque from the voltages and the currents. So in the previous case, we had used the current control to generate the PWM pulses for the three-phase inverter. Here, what we do is we use, in the case of a direct torque control, in order to have a faster performance. If we directly get the information about the flux as well as the torque, we can directly control the motor. So that was the idea of this direct torque control. So we need not have an inner current loop here because we have the flux value as well as the torque value. We need to feed in those values for the system, and then using a switching table, we can control the switches for the any motor of any vehicle or an industrial drive. So these are the different drives that are different control methods that are being used that were being used in industries. Okay. So starting from the fixed speed motors, we have moved on to intelligent EV drives. From the DC drives, scalar, we had the scalar AC drives, which we had seen, the V by F control, and then the vector control. We had the DQ transformation metrics, and then the direct torque control, where we also have different. If you look at these controls, if you look at these block diagrams, what we can see here, there are controllers available here. There you can see a flux controller, a torque controller, a velocity controller. These are the different controllers that we will be discussing later on. So here in this DTC, we have a hysteresis controller in this picture. We can also have PI controllers for the system. So we have moved from the fixed speed motors to intelligent EV drives, where we have different control algorithms being used, adaptive MPC or MPP algorithms, to improve the efficiency of the system. Okay, so now these are the now moving on to the different. I'm not going much into the different industrial motor classification. For completion, I have put this. So we have the AC motors, AC induction motors, AC synchronous motors, and this is important. We have the direct current motors, the brushed DC shunt and series motors, and the brushless BLDC motors, which is very, very much used nowadays for automated guided vehicles, especially in drones. The control mechanism is using a 6-pulse trapezoidal logic, so which is kind of very easy. And the performance wise also, even though there is chattering, the performance wise also it is good enough. And we have servo motors also for robotic arms, which can give high resolution precision for the motors. And for CNC milling machine, pick and place tools, we have servo motors, can be either AC or DC motors can be used. And in the case of stepper motors, these are the industrial motor classification. We can have, we move in discrete steps. For example, in the case of a printer, we move in discrete steps, and we latch on whatever data we have to put in the system. Okay, so these are the different motor types as well as their characteristics. Okay, Now, let me transit to the electric vehicle direction. So, if you look at an electric vehicle, what do you think? Like, how many, like, if when we look at an electric vehicle, the major electric motor that we think about is electric vehicle is a motor of an electric vehicle, either a PMSM motor, an induction motor, or an SRM motor, and kind of things. So, can you say how many motors are available? Electric motors are available in a are usually seen in an electric car. Can anyone say? So, for example, if you want to control the speed of the wind, if you want to push down the window pane, we need a sensor as well as a drive system to control. There are motors involved there. So, servo motors involved at many places inside the electric vehicle, right? So, around 20 to 40 electric motors are available based on the cost of the vehicle. So these are thus EV is fundamentally an advanced electric drive system integrated with batteries, power electronics, sensors, and an intelligent control. Okay. So now, why we have chosen this EV for today's session is, in the case of an industrial drive, we have a fixed installation and a grid powered, mostly constant load. We need not concern about the weight. Cooling is easier. So we have a fixed installation. The grid, the motors are powered from the grid side. We need not bother about how it is being powered. We need not bother about the efficiency of the motor. And for example, in the case of elevator, we can have a regenerative braking, but in most of the cases it is not there. But when we come on to an EV drive, it is a mobile and a battery powered system. So there will be complications which are concerned about the battery management system. High dynamic loads will be there, and we require a lightweight vehicle, and these are certain constraints in the case of an EV traction. So studying an EV drive is more than enough for understanding or improving the research thoughts, or improving the research directions that we have presently we have presently moved into. Okay. So now EVs require additional functions such as battery management, regenerative braking, traction control, and vehicle level energy optimization is also required for range optimization of the electric vehicle. So there are different control algorithms coming up. Okay. So now if you move on to the PMSM, the driving scenarios of an EV drive system. So, if for a small stop and go city launch, that means if a vehicle is moving, going in a at a like stopping and then starting, what happens is that there are concerns regarding the torque ripple reduction for a PMSM or an IPMSM motor. IPMSM is an interior PMSM motor. So, but there are control mechanisms such as MTPA, which can reduce the ripple and improve the performance of the system and ensure a smooth launch for the PMSM motor. So this is why there are a lot of control mechanisms for this. And now if the vehicle is going beyond beyond the base speed of the system, what happens is that there are field weakening methods which reduce the current along the ID axis and overcomes the DC-link voltage limit to extend the high speeds above the base RPM. And for an AC induction motor, during high speed costing, there is a dynamic variable flux tuning method, even though there will be rotor core loss in that, which are to be controlled. So it will drop the excitation to zero, removing all the magnetic drag of the system to save the battery range. And for AC induction motor, if I want an auxiliary axle acceleration, there are methods like indirect field control, though we have a transient torque response for this, which instantly wakes up the secondary axle, providing a rapid throttle response during this when we aggressively overtake another vehicle. So these are certain control mechanisms that are being used in electric vehicles. Okay, so as to have a smooth movement or smooth travel. Okay, so in the case of a BLDC motor, it is usually used in lightweight electric vehicles. In the e-bikes, the River Indy bike that I have at my home is using a PMSM motor. And for example, the Ola vehicle is using an IPMSM motor. But if I have a small vehicle, we can use a BLDC motor because it has a 6-step trapezoidal control mechanism. Using the Hall sensors are to be there. So, but what happens is that there is the torque ripple in the whole system. And the next important motor, which is being like where a lot of research is happening, is the rare earth magnet free drivetrains, which is a switched reluctance motor. Which there are different control techniques available for SRM motors also. Since the PMSM motors are costlier because it is very difficult to because of they are having magnets in it. We have a switched reluctance motor without magnets. So the electric vehicles are moving towards switched reluctance motors, though the control is kind of complex because of the non-linear nature of the whole the inductance profile. And if we go for a deep steep descent, we have a 4-quadrant field control, which maximizes the energy as well as the efficiency of a system, and so that we can safely convert the regenerative feedback and charge the battery, and considering the charge limits of the battery management system. Okay, so then we have multi-motor setups where we can have active torque vectoring loops method, to which mitigates a wheel swing out in milliseconds by calculating the individual wheel slip ratios. That is, separately they calculate the wheel slip ratios, and they try to dynamically balance the vehicle stability without relying much on the mechanical brakes. So these are certain EV traction drives based on the drive scenario, and based on different drive scenario, and based on the control different. These are some of the control mechanisms that were available are put into the slides. We can choose a particular motor for a particular application. Then another important concern while choosing a electric vehicle is, while designing an electric vehicle, a control for an electric vehicle is the torque load of the system. So the vehicle may be climbing a hill, so the tractive effort of the whole system will depend upon the rolling resistance of the system, and the aerodynamic drag, which has a major effect on the torque load, which is because it is proportional to the square of the velocity. And another major concern is the linear acceleration, which is proportional to the acceleration. So how if we have a frequent acceleration, if we are doing a frequent acceleration for the system, we can see that this term goes on increasing. Okay, so this is how we calculate this. Torque load has to be calculated before designing a control for the system. So the control system implication is that the nonlinear time varying nature, that is FAD, which is proportional to V squared, and the unpredictable step changes in road gradient. We know that the road, this is alpha, this is a gradient of the road with respect to the horizontal line. So we have a cos alpha factor as well as a sin alpha factor, which can increase the rolling resistance as well as a hill climbing force. Okay, so these factors are to be considered before designing the electric vehicle, before designing a control for an electric vehicle. Okay. Then there are other considerations also. That means for a smooth drive, we have to go for an anti-jerk filtering has to be done. Then we can go for, because if I want the vehicle, I have already discussed that if I want to go move the vehicle beyond a particular speed, and if I want to have, we can have maximum torque per ampere control, so as to minimize the copper and the core loss, which is in fact an optimization control law. And then we can also have thermal derating control loops within the system, which can reduce the thermal voltage, thermal or temperature, or the which can minimize the stator winding temperature, so which can alert us regarding the stator winding temperature and cool the whole system. So these are some of the other considerations that are also to be considered while designing an EV motor. Now let us move on to the control of different motors. Okay, so this was till now we had discussed the industrial drives, and then we have moved on to the industrial drives. What are the motors used in the industrial drives? And then we moved on to the electric drives, and what are the different motors that are used there, and what are the different control generally available control techniques that are available in the which have been invariably used for various control techniques. Okay, then if you go for an FOC, we can see that once we take the current measurements, we have a current regulator there. We have an inner loop current regulator there. And we have, if we take the measurement, if we feed in the speed, we have an inner loop, we have a speed regulator also. In some cases, we may also require the position. For example, in the case of drones, we may also require the position of the system to be calculated, and from the position we generate the speed. Okay, speed reference. Okay, so these are this is a cascaded control. We have an inner loop current control, then the speed control, and then a position control. So sometimes we can have a torque control here, which generates the required torque here. Generates the required current here. Okay, so now what happens here is that means here, if you look at the inner loop of this machine, it generates the PWM signals which has to be sent to the motor. Okay, so now this inner loop should be fast acting. That means it should generate the signals faster than the outer loop. That is, if the speed regulator will have a lower bandwidth compared to the current regulator. That means this should be ready by the time this sends the signals. Okay, so we should have a higher bandwidth for the inner loop. So this is one of the concerns. These are concerns that we have to cater during the design of control systems. Okay, so let us go into the different control aspects. That is for the FOC. In the case of FOC, we have seen that for the FOC, in order to generate the current, we had a current regulator. We can have a PI controller there to generate the current or regulate the current there, and we can also have robust and adaptive controllers such as sliding mode controllers, model reference adaptive controllers, and also we can have higher order controllers which caters to the safety critical bound of the whole system. Suppose we have some constraints on the system, we have to go for barrier Lyapunov methods also for the control of the systems. Okay, so let us start from the basic control technique, which is a bang control or a manual control. That means if the error is greater than 0, you give a particular value, Umax. Then if the error is less than 0, then you give an Umin. Okay, so this is how you just bang the values across the system. That means less than 0, you put Umax. Greater than 0, you put an Umax, and if it is less than 0, you put an Umin. So what happens that there will be chattering in the system. It will be that means the switches. We definitely know that this controller generates the PWM signals to commands to the to work with the switches, right? So the switches, the frequency of the switches may not be will be very high, and the switches will not be able to respond to the frequent chattering of this control. Then we can also have a dead band here, so that for a particular band we need not have to do anything. So beyond that band only we need to give a control which directs us to the hysteresis band controller, which most of you might have done in most of the projects, which is very familiar for you. We know that if we go beyond a particular value, we have a band of values here, which within that band we are trying to keep the current signal, or we are trying to maintain the current. So this is the hysteresis current controller. So here also we have, if the reference current and the actual current measured is less than a particular band value, then what happens? This lower switch switches on, and if it is greater than that, what happens? This switch switches on. So that is how this switching happens, and the intermediate control is in fact the actual value of the current. Okay, so this is how the switching happens in the case of a hysteresis band controller. So this is invariably used in direct torque control for a rapid torque response during sudden acceleration transient. So this works very fine for direct torque control, though we can see a chattering in the system and torque ripple in the system. So we can have other methods to reduce the torque of the the torque ripple of the system. Okay, so now we will look into the proportional integral derivative control. This is something which we study in our control system, and we have been using for the control of drives. And many researchers or students as well as faculty, they tune the PID controllers in such a way so that the system works perfectly well. So let us just have a look into how this tuning is being done, and why we want to give a particular value, and what are the considerations while designing a PID control, which is a basic control system for the whole, because this is the base of all the controls. And if you look if you look into the DRDO drones and all those things, the autopilots, it's even now is a PID controls. Because if you tune a PID control, it works perfectly well. So now there are a lot of other control algorithms which is working, which are being used for machines as well as drives. So let us have a look into the PID control. So now, what is the P control? We'll start with the P control. We have an error. Error can be speed error or whatever it is. Those we push in the error. We give a high value. We push in the error with the KP. Okay, so we give KP times ET for the system. So our GCS will become the controller transfer function is KP. So this is a proportional controller. We know that KP times ET is a proportional controller. Okay, so we can also have a proportional controller with different characteristics, with a dead band and a controller limit value also. We can also have systems like this. Okay, but we can see that the error signal but now what happens if the error signal is 0? If the error signal is 0, that KP is equal to 0. There is no control on the system. Okay, so that means we may not be able to achieve the value that is required. We may not be able to push in this value to the system. So let us have a look at the body plot, root locus, and the step response of the system, and understand the P controller. So consider a transfer function here, GP. This is a system transfer function, 1 by S plus 10. Now, if you look at the step response, the bottom one is the step response of the system. If you look at the step response of the system, you can see that the step response is the final value. That means this, if you consider a unity feedback system, that is 1 by S plus 10 with the unity feedback system, that is the step response of the system. We are giving a unity feedback. We can see that it has not reached the unity value. This is not 1, it is only 0.0909. Okay. Now, if you look at the body plot, what happens here is that we have an infinite gain margin for the system and an infinite phase margin for the system. And this is about the whole system. We have the poles at S is equal to 10. This pink value is a pole of the closed loop system. So the pole of the closed loop system will be 1 by S plus 10 divided by 1 plus 1 by S plus 10 will be at S is equal to 11, S is equal to minus 11. So that is why here the pole is at, of the closed loop system will be at 11. So this is the body plot of the open loop transfer function. Okay. Look, now I want to go into, now I have given a P controller for this. See here what was, it was minus 20. I have changed the gain of the system from minus 20 to a particular value. I pushed the signal up. Okay, I pushed the signal up and changed the gain of the system. And what I did was, wait. I push the signal and now I think it has gone. It has gone to from minus 20 to 10. That means around 30. 30 dB change has been made on the system. Since we are only changing the KP value, there is no change in the phase, right? There is no change in the phase. But you can see here, now you can see here, if you look here, we can see that in the previous case, the system had reached only 0.08 in 0.2 seconds. But here you can see the system has reached 0.6, 0.7 in 0.05 seconds. So the system has become faster, right? The system response has become faster. So how do you analyze the response of the system? See here if you look at the 0 line and if you come minus 3 dB, you can get the bandwidth of the system. So the bandwidth of the system is approximately 28.9 seconds, right? So the bandwidth of the system has increased. Okay, so this is how you, and the pole has moved to 40. That is 1 by S plus 10 plus this 30. We can add this 30 also, then it becomes 40. So it has gone to minus 40. So now we can see that this bandwidth of the system has increased, but we can also look into the phase lag of the system. It is approximately some minus 70 or something here. The phase lag is minus 70. So when we improve the bandwidth of the system, we are also inducing a phase lag to the system. Okay, so I will show you the next figure and just show you how I am trying to change the KP to another value. See, the KP is changed to from 0 to 5, 10, like that, up to 20. So we can see that the bandwidth is changing. Once the bandwidth is changing, we can also see that the lag of the system is also, there is also lagging of the system. So what do you mean by the bandwidth and the lagging of the system? So what do you mean by that? Okay, so if I introduce a KP to the system, I can improve the bandwidth of the system. That is what I had discussed previously, where the inner loop controller should have a higher bandwidth so as to work perfectly when the signals come from the controller next to it. Okay, but if there is a lag in the system, even if the controller works faster, the system, that means the machine or the electric vehicle, may not be able to send the signals as fast as the controller requests. Okay, so that is the lag. So it comes with a trade-off. That means as we go on increasing the the bandwidth of the system, we can say that the lagging of it lags. There is a lagging in the system where the system may not be able to respond properly. So we have to design the system based on how the system will be able to respond properly. So now if you look at all these figures, so that is about bandwidth and the delay of the system or lagging of the system. So bandwidth, when we increase the bandwidth, there is also a problem here. That means we are increasing. Here we have increased it to 28.9 radians per second. So when we increase the bandwidth, we are able to push in higher frequency signals to the system. that means there will be noise in the system. So when we try to increase the bandwidth, there is also a problem where there will be noise in the system. Okay, so these bandwidths as well as the lagging system should be designed properly. Okay, now if you look into the proportional controller, no way that this proportional controller is going to reach 1. It cannot reach 1. Why is it so? We have varied from 10 to 100. I don't know whether I varied from, though I have written it as 10 to 100. Here it doesn't reach 1. So this is the problem with the P controller. So why is it so? In the case of a P controller, we can see that this is the GP, the transfer function of the system. This is KP. Now KP into GPS divided by 1 plus KP into GPS. We have this closed loop transfer function like this. Now if you look at the steady state error, what happens here? There is always a steady state error for the system. So that is why a P controller will never achieve one unity value for the system. So we need to have, if I want a precision, if I want a motor with precision, if I am going to do an operation, so there should be precision. So we need to go for an integral controller which caters the integral part. Okay, so now let us go into the integral control. So what is an integral control? In the case of an integral control, we integrate the errors of the system together. We just integrate all the errors of the system and then we add it up so that and multiply it with Ki. That is why it is sum of the errors. That is the integral of the errors. It is a sum of the errors at every instant. Okay, so this is the intent. So that means we are also considering the previous errors of the system and we are trying to improve the performance of the system. Okay. So now in the case of an integral error, integral controller, if we plug in Ki by S to the system, we can see that the steady state error immediately goes to 0. Okay, so that is the advantage of an integral controller. So now let us have a look into the system. Okay, now I have taken the same system 1 by S plus 10 and then I have plugged in a controller, integral controller here. That means I have plugged in a 0, the pole plugged in a 0 to the system here, plugged in a 0 here to the system. Now we can see that immediately the the step response has gone to 1. Okay, so we have achieved our steady state error. That means our requirement, that means steady state error is equal to 0. But now can you just look at the bandwidth of the system? There is nothing there, right? There is no bandwidth. Frequency is 0.1. It's even 10 to the power of -1. There is no bandwidth for the system. So the bandwidth is compromised with a 0 steady state error. So we cannot go with the direct PI controller. And in fact, these systems are in fact unstable also if some disturbance comes to the system. Okay, so now we go for a P plus I controller. Then with the same system, I have this function, this body plot. I just push it up by 20. 20 dB per decade. I have just pushed it up. Okay. So what has happened? If you look at the performance, now you can see here, it took 20 seconds to reach 0.9 here. Now, when I plug in a KP, it has taken only 2 seconds to reach 0.9. See, why is it so? The bandwidth of the system has increased. That means if you look here, the bandwidth of the system has become to 1.02 radians per second. And because of that, we are able to get a faster response. Okay, but the system is not having a good bandwidth. So this is how you plug in a P plus I for the system. So we improve it a bit more further. We can see that the bandwidth has increased. Okay, again increased. But if you look at this system, whether we have to also look at the system whether it is lagging. What is the phase lag of the system? Okay, so here it is around 120 or something. 120 or something. Here it is around minus 100 or something. Okay, so this is a phase lag of the system. So the phase lag has increased for the system. That is okay, but we require some bandwidth for the system. But now if you see, we have pushed in the proportional controller, there is an oscillation for the system. The system oscillates. For some systems, these oscillations are okay, because we can, if we need better bandwidth, we can go for oscillatory controller designs also. For some systems, we can have the poles on the imaginary axis, so that is also fine. Okay, now if we look in the I controller, we have seen that there is a steady state error in the system. There is an oscillatory behavior if large value of Ki is plugged in. For all these values, I have given Kp and Ki is equal to 1 only. And there is an integral wind up. Suppose the error is 0, even then error comes to 0 also. What happens is that since it takes a summation of the errors, there will be an integral wind up, and there will be a saturation for the system. So this has to be avoided by designing these systems at the integral wind up. Okay, then now another major application here is, now we have an oscillatory system here. Now we try to reduce the effect of this pole by introducing a 0 very near to the pole. So near minus 1.6 has been put here. This is in fact not a derivative controller. I have put in a 0 to this. So what does a 0 do? It improves it gives in the phase lead for the system. So below this 0 value, when the pole is 0, we have minus 20 dB per decade, and after that this minus 20 plus 20 almost flattens here. See, it can almost flatten here, and once it comes here, we can see that the frequency has improved to 57.2 radians per second, and the performance of the system has improved a lot using this system. Okay, so this is one way of using designing the PI controllers for the system. So we can have a smooth control based on these PI controllers. Okay, so these values, we have to define these values. What is the bandwidth that we require? What is the phase lag that we require for the system? All these has to be designed for the system. Now we have the derivative controller. Where does the derivative controller come in? Like now we have, for example, there is a huge acceleration for the system. Like I am changing the speed of the system. Okay, there is an acceleration. I want to accelerate the system. So what happens? We have to take into account of the change in the error also for the system. So that is why we can include the derivative control action for also to bring in to improve the performance of the system or reduce the oscillations of the system. That means this oscillations happens because there is an immediate change in the system. So we can bring it down using a derivative controller. So sensitive to fluctuations in measured process values. So there is a derivative kick for the system. Okay, now I will just go to the figure and explain here. So here, if I have a P plus I plus D controller, so I have also, for the previous controller, I have also plugged in a derivative controller here. But you can see when I have plugged in the derivative controller, the steady state error has gone below 0.9. Why is it so? Because this derivative has been placed near the pole of the system, the pole that has been induced by the integrator. So the effect of the integrator or integrator effect has been reduced. So we have to change the values accordingly, or move the Kp Ki values accordingly, or go for a PD controller alone to improve the performance of the system. Okay, now for the derivative controller, what I said is, so this is a derivative controller. So this is this is a pulsating signal, and a derivative controller was used to follow the signal here. So the error of the signal is like this. So error is like this. So if you look at this part, we can see that there is high frequency in this part. So since the error high frequency is there, so the derivative output of the derivative will be very high. So these kinds of effects for the system has to be taken care while designing the system. So a derivative always comes with a filter. We can reduce the noise by including a first order filter for the system. Okay, so it always comes with a filter in the system. Okay, so we can reduce it. Okay, and then there is another set point weighting also. Here I have a kp here and kd here. Based on this beta value and this gamma values, I can set the changes in the derivative part as well as the proportional part. So I can change this gamma values and beta values. So I can weight, I can either bring KD to 0, have give a very small value of KD, so that I get the performance of the derivative controller. Okay, so because sometimes I may want to reduce or overshoot of the system. Okay, so this combined controller, so the derivative action has to be filtered in order to make the controller proper and to filter the high frequency measurement noise. So there are a lot of techniques available in the system, and the set point controller has a 2 degree of freedom controller, which can filter out, which can design a proper controller for the system. Now there are other important techniques for tuning these KPKI and KD. So one is a heuristic tuning method, rule-based tuning or model-based tuning. So in the case of a heuristic tuning, we just define the KP values of the system. Initially, we tweak in, like we define the P controller in the similar way as we had seen here. First, we plug in the P controller so as to improve the speed of response, and then go for an integral action and then bring down the error to 0. But we get a poor transient performance and an oscillated response. We then go for a D action if required. So, but these heuristic tuning does not guarantee a robust or a stable performance. Okay. So here in the system, you can see that we can define the specifications for the system. That means I want the performance, I want the step response to lie within this band. I can define this, and then I can tweak around this KP, KI, and KD values so as to get a proper get the system lying within the band that I have chosen. So I can define the values for the rise time as well as settling time for the system. Okay. And there are other methods. You might have heard the Ziegler-Nichols method, Cohen-Kuhn methods, Kappa-Tau methods, and all these things. So let us look into the Ziegler-Nichols method. So in the case of Ziegler-Nichols method, what we do is we take the step response of a system. So based from the step response, what we get is we get an L and a T here. We can draw a tangent connecting to this inflection point. From the L and to T, we can find out the KPN, KP, TI and TD values of the system for a P, PI and PD controller, PID controller. And this is another way using the body plot. If I want to calculate the P, PI and PID controller, tune the P, PI and PID controller using Ziegler-Nichols method. Kc is nothing but the gain margin of the system, that is 28.8, and omega n is this TC is nothing but 2 pi by omega n. See, so we have this omega n and Kc, and that means we have Kc and Ti. So we can easily design this values. This is a body plot of the system. This is a step response of the system. So from the step response as well as the body plot, we can, and using this table, we can easily define the Ziegler-Nichols tuning rules. But it's kind of tedious because we have to just plug in the values and then adjust around those KP, KI, and KD values so as to get a better performance. Okay. There are Cohen tuning rules also, which can improve the KP, KI, and KD values for different performance. Okay. Then now if I want to tune the PID controller parameters KD, KI, and KP, we have the integral of the absolute error, integral of the squared error, or the integral of the time weighted absolute error of the system. We can use these parameters to and minimize these parameters so as to find out the, so let us find out the values of KP, KI, and KD. So let us look how look a buck converter, DC-DC buck converter. So this is L into Di. This is the current equation, and this is a voltage equation. So now we can define a minimization function J such that this current equation is a minimization function which depends upon EK. ETK means it can be the error in the output voltage or the output current or the inductor current. And EU is the change in the controller values. Okay. So now EU is the change in controller instantaneous control value. So we have U of t as equal to Kp into Et plus 1 by Ti into sigma Tk to Tkf. That is the integral part. So Kp plus Ki is there. Kp plus, that is P plus I controller is there. So you plug in this over here and then minimize this whole system. You can use any genetic algorithm methods to minimize this whole system and see how and find out the values of Kp and Ti, because now the J function will have Kp and Ti here. So we have alpha and beta. Alpha and gamma are other variables, because suppose I don't want this part to be, these are weighting factors, alpha and beta. I want this, the change in the voltage at the inductor voltage or the capacitor, inductor current or the capacitor voltage. I don't want to include it much in the minimization function. So I can put in a low value of alpha, but I want a good controller. So then I can increase the value of gamma. So based on the alpha and gamma values, I can improve the minimization function. So this is one optimal PID tuning method that we can use in power electronics or in renewable energy systems. Okay. So now I will just, since this is a renewable energy system course, so I'll just go into one PID controller tuning method where we have the solar panel connected to the battery, and this is an MPPT and buck converter, and we have a PID controller here. So for in order to design a PID controller, the first thing that we have to do is we have to design, we have to model the system. We have to model the system and using state space averaging methods and bring it to a state space model, and then we get the transfer function of the system. Once we have the transfer function, we had seen how to define the controller for the system, right? So this one is important. We have to get the relation between the output, that means the output voltage with respect to the PWM signal, or the output current with respect to the PWM signal. So that is the current. D hat is the PWM signal. That is a duty ratio that has been set. So we can define the duty ratio of the system based on this transfer function. And then this is the output for different values of, for different amperes. When the ampere is changed to 15 ampere, we can see the system is moving smoothly to the corresponding values by designing the PID controller. Okay, so now the PID controllers have been used invariably for a lot of systems, and but the performance wise, if you look into the PID controllers, if I have a chattering in the system, what happens if there is a chattering in the system? There is a chance for instability for the system, or chattering or noise comes in the system. The system will not be usually robust. Okay, so we need to have higher order controllers or higher robust controllers, which I'll be discussing now, which is a sliding mode controller. I'll start with the simple principle of a sliding mode controller. So this is a differential equation, right? This is any system. If you had seen the previous system, here, whatever, if it is a buck converter, that is a differential equation, and any system can be modeled using a differential. So this is a differential equation. So any system is a differential equation. So if I have a differential equation and if I know the initial conditions of the system, I can define the direction through which the system traverses in space. Okay, I can define in which direction if x traverses in space. Okay, so that is that is about a differential equation. So now I have x. If I have an initial condition, it can, okay, I'll just show this picture here. So these are the trajectories in space that x can take. It will take a particular trajectory, and these are called the phase portraits of the system. So any differential equation can follow a particular trajectory, and all the trajectories, if you look at all the trajectories, they will be parallel. They will not intersect each other. So it will choose a particular trajectory, and if we start from here, I can move to one point if the system is stable. If I start from here, I can move to the other point if the system is stable. Okay, so these are the trajectories of any system through which the system moves in. Okay, now in the case of a sliding mode controller, suppose my system is rotating about this. I'm not able to move to the center. I am rotating about this circle. The system is not able to, that means there is a limit cycle in the system. Okay, so it is rotating about this. So I want to bring it to 0, 0 position. So what do I do? So here in the case of a sliding mode controller, what we do is we define a sliding surface here where the trajectories are asked to, that means the trajectories are pushed to this sliding surface. That means we give a control to the system so as to push in the trajectories to the sliding surface. So we can design a switching surface, that is S of x is equal to 0. So this is S of x is equal to 0, which depends. So E of t is the error, E dot of t is the change in the error. So this is any system. This system can be the error dynamics of the system. And so we can have two modes of operation. So we have a reaching mode for this and this initial point. From this, it goes from a particular point, and once it reaches the sliding surface, it moves to the sliding surface and reaches here. That means it pushes, the controller pushes the state trajectories through the phase through the trajectories of the system, and it pushes it to the sliding variable, sliding surface. So this is how a sliding function works here. So this is the idea of the sliding mode controller. So what happens is that I have an initial condition for the system. I move forward. So this I move forward. We can move forward using, that means once I reach the sliding surface, once it reaches here, it moves past the sliding surface because we are giving a controller. That means the controller is a plus signal or a minus signal, kind of an on-off control kind of thing. So it moves past the sliding surface, and again we push in back. Again we push in back, and then finally, once it reaches the sliding surface, it can move through the sliding surface. So this is called the sliding mode. So this sliding surface is defined based on the dynamics of the system. So how do we do that? Okay. So this is sliding mode controller. Is a robust or adaptive nonlinear controller where we define a sliding surface which is S of x is equal to 0. It is invariably used in EV applications. That is why I have discussed here, because it replaces the outer speed. It can replace the outer speed controller to a robust, to reject the external load disturbances of the system. So that is why it is called as a robust controller. So now let us have a look at the system. This is a double integrator, or we can see as a simple pendulum equation. So here we have the position as well as the velocity. X1 is the position and x2 is the velocity. So x1 dot is equal to x2 and x2 dot is equal to u plus f of t comma x1 comma x2. So this is a disturbance that is acting on the system. Now I have this whole system. Now I want to bring in the whole system to a stable point. Wherever I start, assume that this is the error dynamics of some system. Error dynamics in the position, error in the velocity. So I want to bring the errors to 0. So if I want to bring the errors to 0, I have to define a controller, a feedback controller U, so that this error goes to 0. Okay, so now let us have a look at the feedback controller. We know that minus k1 x1 minus k2 x2. The simple feedback control law is here. And when k1 and k2 is greater than 0, I start from x1 is equal to 1 and x2 is equal to minus 1. We can see that it is smoothly going to 0. And this trajectory from -2 and -1, that is x1 is equal to 1. This is the phase trajectory of the system. This is x1, x2 of the phase portrait of the system. From 1 and -2, it is moving to 0. So this is, it moves through the phase trajectories of the system. So this is a phase portrait. We can see it smoothly moves to that point. But now when we plug in a sine 2t to the system, what happens to the system? We can see that it moves around the 0 point, kind of a limit cycle. See, moves around the 0 point. It starts from -1, -2, and it moves around the 0 point, doesn't settle here. So how do we define a controller here? So that is the sliding mode controller that we are going to discuss here. So we define a sliding surface here. We are going to define a sliding surface here, so that the trajectories, once it reaches here, it tweaks in and pushes itself to move into this line. If I define a line here based on the dynamics of the system, I can push in the trajectories to this line. Okay, so this, now I can define an S is equal to x2 plus lambda x1. S is equal to x2 plus lambda x1 is a line that is passing through this center. It is a line that is x2 is equal to minus lambda x1. This is a line that is passing like this. So now what I can do is, if S goes to 0, that is x2 plus lambda x1 will go to 0. That means x1 dot plus lambda x1 will also go to 0. That means when x1, that means x1 dot is equal to minus lambda x1. That is x1 of t is equal to x1 0 e raised to minus lambda t. When x1 goes to 0 as t tends to infinity, x2 also goes to 0 as t tends to infinity. So both, when s tends to 0, we can see that x1 and x2 goes to 0. So that means if I have a line like this and I define a controller based on that line, I can bring in the state trajectories to this line, okay, and bring in the system to 0. So that is how we define the controller. So now S dot, we take the change in the surface, that is lambda x2 plus u. So when we take lambda x2 plus u becomes equal to, u is, now I define a controller minus k sine of x1, that is minus lambda x2 is added here, so that this part goes out, and I have a S dot is equal to minus k times sine of s. Okay, minus k times sine of s, which is k is a constant here, which can be greater than 0, so that which depends upon the values of the sine signum of s. So now if you look at u, you can see that minus lambda x2 is part of the dynamics of the system, and this part is based on the values of the switching surface. Okay, sorry, this is not sigma, this is s. Okay, so this is about the, so now what happens, we can see that the system moves, once it moves to the switching surface, it slides along the switching surface and reaches the 0 point. So we can see that there is the system finally reaches the whole system using this controller. But we can see that based on the value of sine, because this value of sine of s can vary from +1 -1, can change, can be +1 or -1. So based on the change in the error. Okay, so there will be definitely a chattering in the system. We can see the chattering in the system. See, this is the chattering in the system. So that means the controller that we have, u is equal to minus k times sine of s, will also have high chattering. chattering in the system. So this zigzag motion is can be avoided by having a smoother sliding switching control here. Instead of having this +1 and -1, we can go like this. We can have a saturation function here like this. We can go to have a function like this to reduce the chattering. And we can also have higher order. We can also, for example, the switching controller can have can in fact consider something like a integral as well as lambda times e. If I have s is equal to lambda times e, that means it is directly proportional to the error. That means I have only one variable here. If the variable changes, I have both the variables included in the system. Okay, so I can have higher order controllers, higher order systems. I can design higher order systems for the system for a sliding mode controller. Now what happens is, if I want to check in whether the system is stable, I have to use the Lyapunov techniques to see whether the system is stable, and also I have to see at what I can also see at what time the system reaches here using Lyapunov techniques. Okay, so there are also higher full order terminal sliding mode controllers where we can have the sliding surface with two other variables also. So we improve the degree of freedom of the sliding variable. So I can change alpha 1 and alpha 2 based as this goes to error goes to 0, this term goes to 0. This error goes to E2 error goes to 0, this term also goes to 0. But here what the advantage is, I get two more parameters to control the system. So as I can have multiple parameters to get a better controller. So this is about full order terminal sliding mode controllers. So now just I will wind up by discussing about what is a model reference adaptive controller. Now I have a system which I am not able to find the model of any system, the system that I have. So how do you control the system? So in that case, what we do is we formulate the model of the system based on a control mechanism where I have the error between the reference model output xm and the actual output x drives an adaptation mechanism. So that means I take the response of the system, and then I see that the model which I have considered matches the model of the system, matches the actual system. So this matching is done by using optimization techniques. For example, the MIT rule is in fact the gradient descent methods which can be used to reduce the error between these reference model output and the actual output model. So, and Lyapunov stability models can be used. So there are AI based techniques also to improve the performance of the system. Okay, now if the last part, if I don't have an information about the output variables, I should how do I control the system? I am not able to measure the speed of the system. I'm not able to measure the position of the system. So I have to observe. If that means if all the state variables are not observable, what I have to see is I have to design an observer for the system. So the state observers can be designed for are being designed for various systems. We have the basic Leuenberg observer, which is a linear observer, because we don't use this in complex systems, because we have in the case of EV traction systems, we have a nonlinear system. So we usually do not use a Leuenberg observer. We usually go for higher order observers, higher nonlinear observers, such as the sliding mode observer, or we can also have a Kalman filtering, which is invariably being used in different systems. Okay, here, so these are the different observers here. In the case of sliding mode observer, we can see that here we have to bring in IS to this observed value of the current. So these are the different observer techniques also. that are being used in EV traction. And the benefits, these observers are in fact usually robust because the sliding mode systems are robust, but there are chattering problems in this system, but there are super different algorithms in sliding mode control which can reduce the chattering of the system. Okay, this is the basic sliding mode controller here, which has been used here. And then winding up, in the initial part, I started with the foundational dynamics, started with industrial motors, and then went on to the load profile of different industrial motors and how we can optimize the efficiency of the system. Then we went on to the EV transition, went to EV drives, where different algorithms are being used for the control of EV drives. And we had seen the PI controllers, the sliding mode controllers, and as such, only PI controller and the sliding mode controller. We just squeeze to MPC as well as the MRAC and the sliding mode observers. Okay, so this is about the talk of today's session. So if you have any questions regarding the control aspects or anything, please ask me.
Participants, any queries?
As I think the next lecture is coming at 8 o'clock, and I think
Any queries
Sharnyam
from the
sir?
participant side?
I think we can wind up then if there are no queries.
Yes, ma'am, we can wind up.
Thank you. If you have any doubts, you can send a mail to me.
Okay,
Contact
ma'am.
me. Thank you.
Respected ma'am, on behalf of Triple, I extend a heartfelt gratitude for your insightful and inspiring session in today's FDP. Your valuable expertise, engaging presentation, and willingness to share your knowledge have greatly enriched our understanding of the topic. Thank you for your time, support, and contribution to the success of this FDP. We sincerely appreciate your presence and look forward to interacting with you again in the future. Thank you once again, ma'am.
Okay, thank you.
Participants, the feedback for the first session has been posted in the chat box. Complete it, please. Praveen sir, join ചെയ്തോ? Session start ചെയ്യാം.
Yes, ma'am.
Yes, sir. I warmly welcome all the participants to the second session of Day 4 of our 6-day FDP on advanced trends in renewable energy systems and smart power technologies. As power systems become increasingly intelligent and interconnected, technologies such as BMS and SCADA play a crucial role in ensuring efficient monitoring, control, automation, and reliability of modern energy infrastructure. Today's session will provide valuable insights into how these technologies contribute to smarter, more sustainable, and resilient power networks. We are privileged to have Dr. Praveen P. Nambissan, Professor and Head of the Department of Applied Science and Humanities at Sribadi Institute of Management and Technology as a resource person for this session. Mr. Praveen is an AICTE SLA project member and serves as an observer for the National Testing Agency NTA. He holds a PhD from Nurul Islam Center for Higher Education with specialization in energy, electronics, and instrumentation. He brings over 20 years of professional experience, including 15 years in academia and research and 5 years in industry. His industrial career includes serving as an instrument engineer in Saudi Arabia and as a senior engineer for electrical, instrumentation, electronics, and systems at Pentia Water, Goa. His area of expertise include industrial automation, PLC programming, SCADA systems, instrumentation, control engineering, energy electronics, and industrial systems integration, with extensive experience in the installation, communication, and maintenance of automation system in process and manufacturing industries. He is actively engaged in training, research, and industry academia collaboration, contributing to the advancement of automation and smart industrial technologies. With that brief introduction, it is now my privilege to invite our esteemed resource person, Mr. Praveen P. Nambissan, to take over the session. Sir, we are eager to learn from your expertise and insights on the fascinating topic, emerging trends in BMS and SCADA for sustainable and reliable power systems. On behalf of the Department of Electrical and Electronics Engineering and Sribadi Institute of Management and Technology, I warmly welcome you and invite you to begin today's session. Over to you, sir.
Very good evening. Thank you for the nice introduction. I hope, am I audible to everyone?
Yes, sir. Audible, sir.
Okay, fine. Thank you. So, it is like today's topic. I'll just share my slides and let me start along with that one. So, I hope my slides visible.
Yes, sir. Visible, sir.
Yeah. So now I would like to go across the topic, emerging trends in BMS and SCADA, powering sustainability. So before going to that, I would like to thank Sribadi Institute of and Management for giving me the opportunity to present such a topic in the Department of Electronics, Electrical Engineering. Now, I just wanted to say some real-time topics or practical topics to this particular subject. So I just wanted to discuss regarding emerging trends in BMS and SCADA. So of course, we know BMS is building management system and SCADA is supervisory control and data acquisition. So from the name, one, we can say that building management system, which manage the building and with some sort of things, that's it. Then SCADA is nothing but, it is a supervisory control platform, which gives an introduction or which gives connection from the site to the control or automation area. So normally in 2000 range or the year 2000, 2005, mostly we had the SCADA systems, PLC systems, and DCS systems to control the industry. Now, the AI or the emerging trends, the advanced trends has come into picture to enhance the sustainability for power as well as sustainability for the industry automation. So how intelligent control systems are reshaping the reliability and sustainability of modern power infrastructure. So here I will just go across some basic topics, then I will come into the real scenario. So normally the control stack, it includes different sort of wires, like you might be knowing different sort of sensors are available in plant. So like a temperature, pressure, whatever. So all these sensors will be terminated in the marshalling cabinet of the central control. So that means that the entire marshalling cabinet, the rack is full of just wires with some tags. That is the real scenario in the industry. So how we will do the control stack with the emerging technologies, how we are going to handle all these things with the advanced techniques. That's what we are going to see today. So coming into that point, I just wanted to say regarding the SCADA once again, it's like industrial process automation, providing grid-wide visibility, real-time control and historical data logging and distributed assets. So what's meant by grid-wide visibility? It is just like we are seeing the entire transfer grid or transmission grid at a glance, or we can control the grid at a glance from a particular place. So that is, or that can be done by SCADA systems. Now, if you are coming into the BMS, what will be the difference for that? So BMS is like a cell level intelligence managing safety, state of charge, and thermal health to prevent degradation and catastrophic failure. So BMS is like a part which we can control cell-wise in a sense. If you have any problem for a particular area, that will be identified, that will be notified, and we will be rectified very soon. So that is what BMS stands for, Building Management System. It is a small cell type control system while comparing to an industry. So now what is meant by the integration gap? Integration gap includes the disconnected systems, supports unified architecture essential for coordination and grid operation. So it is like, see, blind spots. What's meant by blind spots? You know, see, in an industry, the blind spots is like, now I connected a huge circuitry to the transmission cable or to the transmission system, and connected in the sense we have just imagine phase and neutral we have. So phase I connected, neutral I did not connect because I'm not using it sometimes. So I'm just removing the component, but one cable I have connected to the circuit. Still in my picture, what I say, I did not connect to the equipment. Whenever I require, I'll connect it. But actually, in the real-time scenario, what happens? This will give a parasitic capacitance or electromagnetic interference to the entire circuit that we are just not noticing. That means you might have heard of parasitic capacitance. So it is some sort of capacitance. It will provide some sort of capacitance, or it will add some noise to the circuit. It will add some noise to the grid, etc. So these type of electromagnetic interference disturbance can be reduced by using different sort of techniques. I'll come one by one. So the disconnected systems create blind spots, which we are not noticing in an industry, in a circuit, or in a transmission line. Now, coming to the SCADA, as we know, it is the backbone of reliability. How we can call it as backbone? Because we can monitor the system. It is giving the real-time data and it is as per the standards. That is the main thing. So real-time acquisition means continuous data streams from RTUs. RTUs in the sense of remote terminal units, and the PLCs, programmable logic controls, deliver sub-second visibility into grid conditions, voltages, and breaker states. Okay, what's meant by this sub-second visibility? It's very important term in the case of industry. It is like RTU and PLC can deliver to the status less than a second. That means if I'm connecting a PLC, if I'm connecting a sensor into a system, it gives response. In less than a second, it gives different sort of response, like the signals are continuous. So that continuous signals can be monitored by the real-time data acquisition. And now, beyond monitoring, modern SCADA enables load forecasting. Okay, load forecasting. What's the load forecasting? Load forecasting, in the sense, the prediction of the need of electricity. So in an industry, if it is forecasted properly, how much electricity can be used by the system, that will be identified by the SCADA at the initial stage itself. It will help us to calculate how much power will be dissipated in an energy system or in an electrical system. Now, coming into the open standards, it is like third generation systems leverage IEC 61850 and DNP3 protocols. So coming to the picture, I will tell you one thing, like whenever I'm connecting a sensor to the PLC or a sensor to the SCADA systems, what will happen? There is a communication link. If that communication is proper, then only I can get the signal from those sides, right? So this will be based upon the exact protocol which we need to use. If I'm not using a proper protocol, if I'm not using a proper communication network, this will not work. And one thing, if it is a very nearby system, we can do something at least by cable or something. But even though if I'm using cable or if I'm using Wi-Fi networks, whatever it is, there are some limitations. So the protocol, communication protocol, is mandatory for communicating the signals from sensors till SCADA or PLC, whatever. Now, what does this IEC stands for? It is like International Electrotechnical Commission. Okay, International Electrotechnical Commission, which is giving the instructions, or which is nothing but giving the standards to us. The signal has to be communicated in a particular way. So that is IEC protocol. It is having various sessions or various numbers. So we use normally in the third generation 61850. It's an open type protocol. And DNP3 protocol. What's meant by DNP3 protocol? It is like distributed network protocol. So distributed network protocol, in a sense, we use different sort of networks, which we can say it as whether it is different sort of like distributed or centralized protocols, whatever. So we normally go with DNP3 protocols for SCADA integrations. So that is nothing but SCADA, the backbone of reliability. Now, coming to the topic, which is nothing but smart grid. So in the smart grid, the overview, first we need to understand what is smart grid. We are hearing the word smart grid everywhere. So we have to be clear what is exactly the smart grid. Smart grid is an advanced electrical power system which combines traditional power grid with digital communication. So what is meant by digital communication? Why we need digital communication over there? That is one point. We are just going to discuss about that. Then sensing, automation, and control strategies for what? Improve the efficiency, reliability, security, sustainability of electricity generation, transmission, and distribution and consumption. So we are going for digital communication. I'll just say you an example. See, when I need to, like, hope you will be having the term, like some, I'll just say an example, like there is some motor, okay, there is one motor. So the motor has to run at least by 90°, then 180°, then return back. So we normally call it as stepper motor or servo motor, etc. We have two types of motors, right? Stepper motor and servo motor. So in the case of servo motors, we normally give some sort of pulse for exact pointing to the rotation, exact pointing to the rotation. Like now you might be knowing the water purifier systems. So water purifier systems, in a sense, we have a cartridge, right? We have a cartridge. So this cartridge will be manufactured in the reverse osmosis plants. Reverse osmosis plants. And if it is, if I'm going for a drinking water purpose, it is very small. The cartridge, you can see that it is a very small cartridge. But if you're going to an industry like water treatment plants and all, this small cartridge will not work. There it will work a big diameter pipe which will act as the shell of the cartridge. That shell will be winded with resin chemical, and it will be like a thread. It will be like a thread winding on a mandrel. So that size of the thread which comes through the comb will be determined by the servo motor, which will be determined by the servo motor. That, in a sense, we are giving some inputs. The distance between the threads which we are winding on the mandrel will be based upon the zeros and ones or the pulses which we send to the motor. That much accuracy we need in the case of digital communication. We have a lot of examples in digital communication as far as communication is concerned, like signal communications. So this is the real-time scenario which happens in a plant for the electrical case. Now, what are the key components of a smart grid? Key components. Key components includes the smart meters measure and communicate electricity usage in real time. So you might be heard about our KSCB, right? Now, they are saying that from 6 to 10, if you use the current, it will be charged more. How they knows that when I'm using that? That is one point, right? So that means they are training their system into advanced techniques where the usage is happening and when the usage is happening to the particular node. So smart meter, we are expected to get the smart meter as soon as possible from our government, right? Then next is sensors, intelligence and electronic devices. So monitor grid conditions such as voltage, current and frequency. So as we know, these are the main parameters, voltage, current and frequency. I'll come one by one to that. What is the purpose of frequency? What are the different techniques to control the frequency? And why we are controlling the frequency in a plant. I'll tell you one by one. Then coming to the communication networks, it enables two-way data exchange between utilities and consumers. It is just to understand me and the system and system and me. That's it. So that is what communication networks. And SCADA and energy management system monitor control grid operations. Then distributed energy sources. It includes solar panels, wind turbines, battery storages, and electrical vehicles, etc. And advanced control systems. These all are the components of smart grid which automate fault detection. Very important. Fault detection, isolation, and service restoration. Okay, service restoration. Fault detection, in a sense, I will say you an example from basic signal side, which is nothing but PRBS, pseudo random binary sequence generator. So pseudo random binary sequence generator, which will give pulses as 1, 0, 0, 1, etc. The binary sequence. So if we are having a DUT, device under test, I'll just send a signal through the DOT and I will get a result. And I will send the signal which comes from the PRBS also through the same system, and I'll get another result. If two results are getting matched, then I can say that the system is perfect. Otherwise, the system has some anomaly. That means the system gets malfunctioned. In an electronic side, if we say we normally use it in ICs to test the device. And if it is an electrical side, the major electrical wirings, which we send some signals to it, and we will be checking whether it is delivering it properly or not. Now you may ask, we have 220 volt and we have 400 volts. How we will give these voltages to the networks and how we will be getting the output? We have devices. So these devices, what they will do, you might be heard about CT and PT, right? Current transformers. So normally how we were measuring the normal in laboratory and all, we will be connecting ammeter to get the current. But in an industry, if you go, we cannot connect ammeter in a shelf or rack where the thousands of wires are connected. So there we use CTs. And that CTs will give the current, and it will be transferred into digital pulses for the accuracy purpose. Then we'll be getting into the display. Okay, this is what really happens. So these are all the components of smart grid. Now, guardian of the battery era. So now we are living in the world of EV. A lot of vehicles we have. Okay, a lot of battery used devices we have. So main thing is our vehicles only, EVs, electric vehicles. So normally if I buy a vehicle, electric vehicle, what is the main point which I focus? In one charge, how much kilometer or how many kilometers it will run, how much it will run, correct? So that is, I'm focusing into the capacity of battery. Now, if I'm coming to the smart grid system, what will happen? If it is monitored by BMS, what I will do, I'll go across SOCs. Just I coined the term in the first slide, SOC, state of charge. State of charge, in a sense, is a precise real-time tracking to optimize charge discharge cycles and extend battery lifespan. That means if I'm having charging and discharging for the battery in a proper way, I can increase the span of the battery. Now you may think that in our mobile, sometimes, okay, I'll get 70% of charge, then I will disconnect, then I will come back to 30%, again I will charge. You know, in every mobiles, what they do, they are having some algorithm now. If I'm continuously charging the mobile, that also will detect. And if it goes below 20, I'm giving charge, then it will note first time. So if it goes below 20, I'm getting battery will say that I'm getting charge. So if it goes above 80, I'm switching it off. So these 2 points it will notice first time. If I'm following at least 10 to 15 times, the processor will have some algorithm for it, and it will check whether this is perfect or not, or that device will understand if it goes below 20, I'll get charged. If it goes below, above 80, I'll get charged. Such type of optimization algorithm which we are using for SOCs now, state of charge. The battery which we are using in the grid places. Now, it will affect the health of the system. How? State of health. Continuous degradation monitoring to predict end of life and schedule proactive maintenance. One thing, if I'm continuously charging a battery, of course, its lifespan will go, as we know. Correct? And more than that, the preventive maintenance is very important. preventive maintenance. The battery preventive maintenance in the smart grid is very important because preventive maintenance what? Otherwise, it will go the total failure. It will go to the total failure. So to prevent the total failure, we are going forward to monitor the health of the battery continuously. That is what state of health, SOH. So these are the points which we come across battery, and these are the points which we are controlled by BMS in the system. Then next is thermal management. Thermal management in a sense, rack level temperature surveillance to detect hotspots and prevent thermal runaway events. So now I will tell you one thing, how to give the thermal, energy loss, how to find the energy loss in the network. Very simple case. Just I have a fan, a ceiling fan. Okay. I have some electrical connections in the panel. So if you take the thermography gun, okay, thermography gun in your hand, and if you are focusing into it, the connections, where the connections happened, the electrical connections happened, it will turn as red, then orange, then yellow, then green. It will show different colors based on the heat dissipation in the system. The same way, if you are focusing into the ceiling fan, the motor where I focus, that motor will show it as orange or red based upon the working time. So that is thermography technique. Normally the energy auditors in the industry uses. So if I'm coming to the smart grid system, the thermal management is mandatory, of course, because we have battery, we are going to charge the battery. If the temperature is more, of course, it will affect the health of the battery. So that temperature has to be monitored by a temperature sensor, which is connected to BMS, which will save the battery if it controls properly. Now, next thing is round trip efficiency. Maximizing energy throughput in a complex BES environments with minimal conversion losses. What is meant by battery energy storage system, BESS, battery energy storage system? What is the round trip efficiency? It is maximizing the energy throughput in complex environments with minimal conversion losses. That means from that point, when we are utilizing the energy from the battery, it will give a precise, optimized value to out. That means for usage. That is what round trip efficiency. That means during charging and discharging, it will have a constant output. And it will be optimized by different sort of algorithms. Different sort of algorithms. You might have heard about MPPT and all, maximum power point tracking algorithm. A lot of algorithms are there to optimize the battery now as well. Now, I'll go to the architectural diagram of modern power plant. So it's a 4-layer hierarchy defines how data and control flow from physical assets to enterprise intelligence. So we have first, I will tell what is a layer 1. Layer 1 is sensor, inverters, meters. Sensors can be different. Sensors can be for measuring temperature or pressure or humidity or any environmental parameters where I kept the smart grid systems. That ambient conditions will be sensed by different sort of sensors, which we can call it as IoT sensors as well. Internet of Things, we are using sensors, right? So the same thing which we can use it for power plant as well. Only thing is the ratings will change. That's it. The concept is same. Now, when I'm coming to the inverters and meters, it is like inverter. What's meant by inverter? From DC to AC. Normal, the conversion is from DC to AC. So that DC to AC rectification, as you know, AC to DC, and inverter is from DC to AC. So when I'm converting DC frequency from 0 to 50 hertz, what are the possible changes will happen? What are the possible losses will happen? We need to know. So that will be connected by the power devices in the electrical engineering. You might have heard about IGBTs. I will tell you how the IGBT comes into picture when controlling happens in the coming slides. So next I'm going to the layer 2. It is nothing but local logic, which is having PLCs, okay, BMS, controllers, and remote terminal units. The sensors will be normally in an industry, how it happens, from the sensor, it will go to the field termination devices. Then it goes to junction boxes. From the junction box, through the cable, it will go to the central control room marshalling cabinet. And from the marshalling cabinet, it directly goes to PLC. And PLC is connected to the HMI, which is nothing but the SCADA. So now, as you know, see, our engineering college, just imagine 4 buildings are there, 4 blocks are there. One is electrical, one is mechanical, one is civil, etc. So for one block, we will have one PLC, just imagine. Another block will have another PLC. So the total 4 blocks will be handled by a central system, which is nothing but DCS, distributed control system, which is giving the control to the entire PLCs. So SCADA, which is going to supervise the the inputs, how it functions or how it controls, then it comes to the history. And it will give a perfect graph to us how the sensor works in a plant, in a grid, in a smart grid system, etc. Then next is intelligence. That is important here. Till layer 3, we have all these things in plant. But layer 4, which is EMS or AI optimization, which we are giving to the system to get maximized output with the minimum resource. That's the point. With the minimum resource, I'm going to give the maximum output. That is the motive of modern power plant. So that optimization, how can we bring into the system? So that is the 4th layer, which happens here. Now I'm just going to the data deluge. So what's meant by data deluge? How we will solve it? Its utility scale storage generates millions of data points daily. The challenge is transforming raw telemetry into actionable intelligence. See, I'm giving a signal, very simple. I'm giving a signal to the system and some other signal also coming into the same system. Thousands of signals are coming into a system and the system is getting confused, which has to be gone first to the output. So that priority, how we will solve the problem? By using what? Our intelligence. That is important. So how the data deluge will handle in an industry, that is nothing but high volume telemetry. So managing thousands of data points per BESS installation demands scalable historians and edge compute preprocessing. Edge compute preprocessing. So that means you might have heard multiplexer and demultiplexer. Where we are using multiplexer, we have several inputs and one output based on the select line. In the same way, we are having high volume telemetry like remote terminal devices in the smart grid, remote terminal devices. And from that remote terminal devices, each cables will go to the rack. And from the rack, we are implementing the system, the algorithm, based on the algorithm which we implement to the system. It will prioritize which input has to be reached or which input has to be processed. It comes to all. So that is high volume telemetry system. So which is there which is there in different plants, because many inputs are coming and we just wanted to select one. That's it. Now, next is predictive modeling. What's meant by predictive modeling? Shift from reactive alarms to condition-based monitoring, predicting failures before they impact availability. Very simple. It's like when I'm giving some sort of signals to a device, some signals will be very feeble, some signals will be strengthy one. Now, could you please tell me, if I'm having a signal, if I'm having an electrical signal and a control signal, normally we know the control signal will have less amplitude. If I'm taking a control signal cable along with the power cable, what will happen to the control signal? Any idea? That means the control signal will be affected by the field of power cable. So now normally what we do in industry, we make it orthogonal. If we are making, if the crossing or something is coming, we will make it orthogonal. Then in the 90-degree, the flux will be cancelled and the power signal will be separate and the control signal will be separate. So this type of designs and this type of modeling in the system, smart grid system, it's very much mandatory, and which we can call it as one type of predictive modeling. Then next is protocol standardization. What's meant by protocol standardization? Protocol standardization includes unifying disparate integrator protocols, Modbus, CAN, IEC 61850, we already discussed. CAN in a sense what? What is meant by CAN? Controller area network. It is also a type of protocol to communicate. If I'm not using a standardized protocol in the system, the communication will not be a good one, and we will lose several datas, and the data will be lost, and finally we will be in the catastrophic failure. So protocol standardization, high volume, how we will handle, and predictive modeling, these are the main techniques or solution techniques for the data deluge in a smart grid. Now, the sustainability pivot. What's meant by the sustainability pivot in the system? Two-way power flow. So we know power flows, right? Okay, bidirectional power flow. High renewable penetration requires SCADA and BMS to manage bidirectional energy flows, grid forming inverters and frequency response. That means we have to have a clear monitoring on two-way power flow. That means the power has to, from source to target, we cannot say source to target, point A to point B and point B to point A if required. That has to be monitored because there are a lot of circuits, there are a lot of connections will come. So when I am just taking a bidirectional flow, it will not be a good idea if I'm not having a proper design. So we should focus on design if we are focusing to the bidirectional flow. Now, what's meant by virtual power plants? It's a granular grid control aggregates distributed energy resources, rooftop solar, BESS and EVs into dispatchable virtual assets. Normally, as we doing virtual power plants, we have the grid control. You might be knowing we are having rooftop solar, and whatever the energy we stored, which we are using for house or domestic purpose, then the remaining energy we can send it to grid through a circuit, right? So that is also one of the bidirectional power flow method where we can store the energy, where we can save the energy. We are giving electricity to the electricity board, KCB, whatever. So then next is demand response. Demand response is nothing but real-time SCADA-driven demand. Response reduces transmission losses and defers costly infrastructure upgrades. I'll tell you this thing, sustainability period. Why we need the term sustainability? See, I'm having a storage of 1 megawatt. In that, I'm using only half of that, 50%. The rest 50% has to go to the line. Just imagine 50% I'm using, 50% I'm sending back to the line. If I'm not sending 50% as per my concept, the sustainability will be lost. Sustainability is nothing but I have to focus how much the power flow will happen, what will be the safer amount of power which I can flow from the generation side to the target, and I mean target in the sense where the rooftop solar or what it connects and back. So this sustainability we have to include in the case of our power systems. Now, the cyber security imperative. So when I am considering AI or when I am considering emerging techniques, advanced intelligent techniques, what are the threats which comes into picture? The threat landscape includes, it is like as SCADA and BMS migrate from isolated serial networks to IP-based wide area systems, the attack surface expands dramatically. Critical infrastructure is now a prime target for nation state actors and ransomware groups. See, where the wars and happens, normally we destroy the power systems first. Because if the power system fails, every communication fails. The same way, the threat landscape, the people who are doing all these things, they'll be first identifying where I can intrude into the system, in which point I can intrude and how I can destroy the system. So if I'm having a proper algorithm, if I'm having a proper system with a higher security, then they cannot enter. Otherwise, it is not like a normal antivirus in a system and which we are protecting the system. No, because we have the smart grid, which we cannot making into a home or a particular area. It is widespread. So in the widespread area, if the system I connect, I should know, is there any open source or any open point is there, or anyone is connected, anyone intruded, that should be identified. So that has to be taken care of with the cybersecurity systems. So you might be heard about the cybersecurity area, which is booming like anything. But thing is, this cybersecurity is one of the major part, or which plays a major role in our grid animation. I mean, grid automation, sorry. So now, I'll just say some points to that. Network segmentation. Isolate the OT networks from IT using DMZs or demilitarized zones. Okay, demilitarized zones and unidirectional gateways. Unidirectional gateways. So actually, the OT network, in a sense, operational technology networks. So if the operational technology networks uses some IT functions or maybe some software or maybe some particular program to prevent these type of hazards, using demilitarized zones. Okay, we have to create the unidirectional gateways which we have to protect. That means the entire smart grid over the nation has to be protected from the server head. That server head has to be like the controlling system should have a proper network segmentation, and each network segment has to be protected in such a way that it is like a militarized zone. If it is demilitarized, of course, what will happen? the operation technology will not be much effective. Now, next is encryption. So this point, as we know, encryption of data. Where you have seen the encryption, the word in WhatsApp, you might have seen end-to-end encryption, right? So what's meant by encrypting? The data encryption. That means, in a simple way, I'll say, I'm protecting a data with some key. So if that key is using to open that data, or if I'm using that key only for that data, then only I can access the information. Such type of encryption will be enabled node by node in the smart grid system. Node by node. Now you may think in node by node how we will implement. We will have a clear-cut picture from the SCADA where the connection happens, where the branches will occur. So in each and every branches, this will be monitored by the encryption algorithms. So which is nothing but TLS 1.3 and AES 256 bit. If I'm encrypting with the 256 bit and all, that will be focusing that much points like zeros and ones, which you might have heard that, 256 bits. So that much protection I can give to the system. So no one can unlock it and no one can steal the data. No one can intrude into our system if I'm using that encryption methods. Now, next is zero trust architecture. Verify every user, device, and data packet. No implicit trust within the perimeter. See, in a smart grid plant, if you go, there are a lot of restricted areas. It's not like our electricity board. There itself, we have the restricted area, right? It is not only based on hazard. If anything happens to the system, the entire power will go off. So the zero trust architecture, in a sense, we should not trust anyone in the network. That means every user will be verified and then only he will be allowed into the system. So that is the cyber security importance when I am considering the smart grid systems in the industry or plant. Now, future horizon. So self-healing grids. What's meant by self-healing grids? The next generation power system will detect, isolate, and recover from faults autonomously. That means if any error is there in the system, it will automatically detect there are some error. So we have to clear it, and it will clear, then it will go ahead. But there is some limitations in that. So if line got break, then that type of self-healing techniques will not work. But some types of earth leakage happens, then it may alter the line. It may alter the line or it may bypass the line. That things will be there. How they will come to know the earth leakage is happening in the grid? Based on the system integration. So minimizing outage duration and maximizing renewable utilization. This happens. Detect, isolate, and restore technique. So hope this is understanding for you. Future horizon self-healing grids. It is like you can trust up to 60 to 70%, not more than that. Because a lot of wounds are there. Wounds in a sense, a lot of errors are there which a grid cannot heal itself. Like the wire break. We cannot do that. It cannot heal itself. It may bypass the line, but we should have that much cost or budget to bypass the line, correct? So that is somewhat 60 to 70% it is fine. Otherwise, no. Now, the call to action, break down the silos. So integrate BMS, SCADA, and EMS to the unified architecture. Fragmented systems create risk, cost, and inefficiency. So if I'm controlling BMS, SCADA into the system, if I'm integrating SCADA into the system, hope this the slide is visible, right, for you? If any error
Yes, sir, visible,
occurs, you
sir.
please let me know. Yeah. If any problem is there, you please let me know because heavy raining is here. So it's
Okay.
like the call to action, break down the silos. So integrate BMS, SCADA, and DMS into unified architecture. So if I'm integrating all these things, of course, we can that architecture can reduce the risk, the efficiency, I mean inefficiency, everything I can reduce. Call to action. Break down all the inefficient things. We can break it down and we can make it into the unified architecture if I'm integrating all these things. Then prioritize the interoperability. Prioritize the interoperability. I'll tell you best example for it. Before, many mobiles we had with a different sort of chargers, right? Different sort of chargers. C-type charger, small type, pin type. Now everything, most of the case, except iPhones, rest everything is like C-type. So that interoperability should be there in the protocols as well when the smart grid automation is concerned. So that is what prioritize the interoperability to ensure long-term grid agility and vendor independence. So it's like I have to communicate with the standards. I have to communicate with the network by using the protocol. It's like a common protocol. So there is no separate type of protocols, but the protocol will have its own security. That is must. That is there. Then think digital first. The next generation of power is not just physical, it's digital. So invest the data infrastructure, cyber security, and AI-driven optimization today. So that means the optimization we normally have optimization. Optimization, I'll tell you an example for optimization. Just I will say, I'll go to a project. We have a solar panel. That solar panel will focus into east in the morning, and it has to rotate from east to west along with the movement of the sun. Okay, till evening, it has to move. So based on the incident ray, the panel has to move. So when the panel is getting moved, there will be some slight changes. That means the incident ray has to reach, then it has to process, then it has to move back, correct? So that movement can be optimized by using algorithms. That means smooth movements can be brought for the panel by using algorithms. So such type of algorithms can be implemented into the system if I'm going analog and digital. And if I'm going digital, it will be much more perfect. That is the difference. Now, reliable power systems for biomedical field. So biomedical field, in a sense, I will explain what is meant by biomedical field. Always on or bust. Very simple. If the system is not reliable in the biomedical area, that system will turn off. That means if a patient in the hospital is not getting the proper care with the power system, reliable power system, what will happen? It will go to the danger, right? Otherwise, if system is working, then he will come back or she will come back. So reliable power systems are more, or it is required more in the biomedical field while considering into any other, because it saves human life. So in healthcare, power is not a utility, it is just a lifeline. So this presentation explores what it takes to design, maintain, and protect essential electrical systems in medical environments where failure is not an option. Because we don't have an option to get failure. If one of our relatives is in hospital, and if hospital says that there is no power, there is no reliable power during operation, will we accommodate? No. So that type of reliability we require. How we can bring all these type of reliability? So The seconds matters. So patient safety, equipment protection, then EES and IT backup. EES in the sense essential electrical systems. It has to be backed up with the proper uninterrupted power supply. If I'm connected to the smart grid, it has to provide the power. It has to provide the power with ultimate protection, ultimate stability. Then only the patient will be safe. I'll go to the example. So normally, because of this, the outage reality, it shows 17% of organization gets affected without the, the reliability of the system is less. And because of that, 17% organizations are affected. And most, it is like the data sets which I used, which I got it from internet. It is not our data set. But the data set itself says that because of the power issue, 17% affected and impacted 5% and 89% of superstorm Sandy. In the hospital, if anything catastrophic things are happening, disaster is happening, that time power will not be there. So that time the outage will be like 89%. See just where we are. 11% only we can save. If the power is getting failed, directly it hits to 89%. So we have to have a reliable system. That is what the smart grid brings. Now, at extreme weather events are increasing in frequency and severity. Your backup power strategy must evolve accordingly. That's it. Then emergency power is a system, not a generator. It's like construction and commissioning. Install components, verify integrated operation. Of course, we are we are giving the construction, we are commissioning the system, and we are integrating all the options. Then it goes to different sections. Different areas like inspection and testing, perform full system test to reveal vulnerabilities. Then ongoing maintenance, schedule preventive upkeep and capacitive checks. Now thing is, see, just an MRI system, MRI scanning system. If a patient is there, the MRI is on and the system works. And next 2 weeks, there is no MRI cases is coming, then the system will be completely off. When the patient comes, what will happen? The system will not work. Less chance to work, lot of problems will happen. It is an electrical system or it is an electronic system. Lot of problems will happen if the system is not doing the maintenance properly. So it has to get the maintenance in a scheduled time. So that has to be there. Then planning and design, define system requirements and redundance strategy. We have to have a backup for the particular system and especially in the operation theaters. If one light fails, the other light has to do the same way. The grid has to give the constant power source, reliable power source. Now, what the system must keep running? It is one is life safety, then critical care, and emergency response. So, fire suppression systems and support infrastructure for response team must remain fully operational during any outage. This thing you know already, because in every building you can see the fire alarm systems are installed. If anywhere it is not installed, they are giving the permit to operate the building. Why? Because life, to save the human life. So emergency response should have a proper communication with the platforms where it gets monitored. Normally, wherever or whichever the system is, if it is an operational theater or if it is a mall or if it is wherever, these things will be monitored properly in a continuous or control room. SCADA operated control room, SCADA powered control room. There I can see which system is running perfectly, which system is not running perfectly. Based on that, I can take actions as well. If the prioritized, the preventive maintenance schedule is coming nearby, it will intimate us. The schedule is coming closer. The preventive maintenance is coming closer. You have to do the preventive maintenance. Whole system follows this. Why? Because we need the reliable systems to save human lives. So these are all coming under our smart grid systems. Now, what we go, even if it is a critical care, now just imagine it is a pharma firm. There also, the critical things are the packing, medicinal packing or medicinal, that means vials are just manufacturing. Everywhere we have to have a proper environment for it. Otherwise, we will not be, or we will get affected very soon. Now, utilities fail, weather happens, humans make mistakes. Of course, if utilities fails, if anything happens to the weather, of course, we will be doing some mistakes. We'll be doing some mistakes. So, I will come to the major term for today's presentation, which is nothing but resilience. What is meant by resilience? Resilience, in a sense, I can just give a definition, which is nothing but it's the ability of a system which can overcome the failure. Which can overcome the failure. That is called as resilience. So resilience, the resilience, why I focus this term, because a lot of many persons in this presentation will be doing their research or completed their research or they are doing MTech or whatever. So like we have a lot of options, a lot of research gaps in the term resilience. I will just show you that. Whether the screen is visible for you? Yeah.
Yes, sir.
Yeah, can you see the IEEE paper which I'm showing here? IEEE transaction paper.
Yes, sir, we can see, sir.
Yeah. So in this, see, method for analysis and quantification of power system resilience. This paper has an abstract where or what are the main topics we have in the smart grid and where the power loss happens, power reliability is getting less, and how it gets overcome. I mean, how we can overcome the points which we are lacking. So I'll just scroll this. So this is the paper, this is the research paper which we need to focus in the future. One of the major paper, and I will show you the slideshow again. So I think I'm visible for the slides, right? Yeah. Yeah, fine. So my slides are visible now?
Yes, sir.
Yeah. Fine. So why I showed that paper, it is just to make you understand the IEEE persons or the researchers mainly focus the term resilience in the smart grid. So I'll just give an introduction on this paper. It provides the comprehensive review methods for analyzing and quantifying power system resilience, focusing the ability of power system to anticipate, withstand, recover from and adapt to the high impact, low probability events, HILP. Okay, high impact, low probability, such as extreme weather, cyber attacks, and equipment failures. So the authors, what they have done, they distinguish resilience from traditional concepts such as reliability, security, and robustness, emphasizing that resilience includes not only disturbance resistance but also rapid restoration, recovery, adaptation, and learning. And the paper also introduced resilience framework covering pre-event, during event, and post-event stages. See, it highlights the importance of smart grids, distributed energy sources during pre-event, during the event, and after event. Whether it is high impact, low probability, or low impact, high probability, LIHP, HILP or LIHP. So what is this low important? I mean, I will tell you in detail. So when I'm scheduling a smart grid automation, whether I face the problem of reliability, whether the system can self-heal pre-event, during the event, and after the post-event. That is what the paper is. Now, what they have done is they have just given a graph. They are still in the transaction side. So what they have done is during pre-event and working time and the post-event time, how the system performs. They have just taken a deck. That's it. And they made the paper, and they told that the smart grid have an automation way, and it can overcome the issues which comes across with the resilience parameters. Resilience parameters can be of anything, like maybe temperature or maybe some sort of physical damage, anything. But self-healing, I told already, self-healing is up to 60 to 70%. So here in the future research opportunities, we have development of advanced resilience metrics. If you are focusing into that paper, and if you are focusing into the point of development of advanced resilience metrics, it will give you the more supporting way how we can make the system overcome such type of issues. How the system can overcome such type of issues. Then I already explained about the cyber attacks, right? So cyber physical resilience assessment. So what are the possible way of cyber attacks? How it can be prohibited from the system? How it can be blocked from the system, etc. The next is integration of renewable energy and microgrids. Already we have done the smart grid system, but thing is the resilient operation strategy is not involved in that. We have done the things, but most of the grids, we will not have the exact control strategy. We can have different sort of algorithms for it. If you are changing an algorithm, you will be getting a good response better than the previous. That's it. Now, next is AI-driven prediction and operator training. So that is employ big data analytics, machine learning, and advanced resilience-oriented operator training simulators to predict hazardous conditions and improve emergency response capabilities. So if you are having a research area in the resilience, you can include or you can recheck the parameters once and you can make the research better. So these are all the area which we have. Then critical infrastructure and interdependency modeling. So interdependency modeling includes, it improves the method quantifying interactions among power, communication, and transportation, water, fuel infrastructures during resilient events. So the resilient factors, when it gets affected, I mean, when the resilient factors affects the smart grid, so a lot of interdependency factors will come. How we can model all those things, how we can control all those things and get a better controlled way of smart grid. So these are the future research opportunities in that. So this is just see resilience, how it is happening, pre-event, during event, and post event. So this is like a training tool where I can tell you what is this training tool. So in normal power system, how we do the training tool, how we will implement this training tool. I'll just tell you what is. I'll just say the abbreviations first. What is this? Okay, API to TRTT. TRTT is Tactical Resilience Training Tool. In a simple way, if I tell the parameters which I'm considering here, okay, parameters which I'm considering here is communication protocols. And second thing is different sort of sensor inputs. And the next is the time. I mean, the parameters like frequency, voltage, current, etc. So based on all these things, we integrate, and by using this tool, we are going to overcome the the problems which comes into the grid. Okay, I'll tell you one by one. I'll just have some wordings here. I'll say you what is API, TRTT, etc. So like API or TRTT, like API in a sense, application programming interface, which we are using. Then when I'm coming to the CCM, CCM is collaborative communication module. Collaborative communication module. In that, I'm getting inputs from various sectors, and I'm giving into PSM or ISS. So what is PSM? Power system model. Okay, power system model, and ISS in the sense intelligence support system. It is just like it CCM access the inputs, and PSM will do the power system modeling based on the intelligence support system. Now, what are the types of dynamic RMS models, dynamic EMT models? Okay, so what is meant by dynamic RMS models? In the root mean square value models only, dynamic RMS models. Dynamic EMT models as well we have. Okay, so if I'm having these two models, I mean dynamic RMS or dynamic EMT models, okay, actually the system is getting inputs from CCM and it process. And based on this process, it is giving back or give the data to the storage. Okay, give the data in the sense of power to the storage in the sense the battery. So if the modeling is happening dynamically, what happens? The battery will have its own algorithm to charge from a minute point, like just imagine from a 5% to 95%. Just imagine 5% to 95%. Even though the value varies, it won't go below 5 and it won't go below, above 95. So that is somewhat I can explain dynamic RMS models. It is, if I'm using that tool, you will be getting more benefited, but we have to study a little bit regarding the API tools. Okay. Now that is what we are happening. We have to go to the training tool, and which we are integrating some sort of inputs, sensor inputs we are integrating, then protocols we are checking, and battery draining system we are monitoring using, etc. Okay, so all these things are coming into the picture, and I'll be okay. So that is the TRTT tool, which I am going to explain. Now, I'll go to the next slide, the best practice designs. Okay, best practice designs, which prevent the best practice designs which prevent cascades. What's meant by cascade? Okay, cascade in a sense, cascade in a sense, we can call it as. I'll just go 1 second. Okay. So I will do one thing. I'll just go from the current slide itself. I will cascade. Cascade in a sense I can make you into that. Multiple utility feeds. Okay, multiple utility. I'll go to that cascade techniques. Okay, multiple utility feeds. Diverse power sources with main tie device arrangements that switch automatically or manually reduce single points of failure. Okay, single points of failure. That means diverse power sources with main tie devices arrangements that switch automatically or manually reduce the single points of failure. The next is portable generator connections. Pre-engineered connection points allow rapid deployment of portable generator sets when permanent systems are stressed offline. Then next is electrical safety by design. Portable connections must be designed with safety interlocks, proper grounding, and clear procedures to protect personnel during emergency hookups. So thing is, best practice design includes multiple utility feeds, diverse power sources with main or device arrangements which we have or it has to switch automatically, then portable generator connections we should have, then electrical safety by design also we should follow. Then flooding in water, it is like silent reliability killer because water finds the lowest elevation always, right? So we have to place the critical equipments above the flood zones anytime. So all these things are coming under the silent reliability. Then two reliability philosophies also we have for generator sets, okay, which includes parallel generators, then single generator with load shedding. Parallel generator includes multiple units running in parallel with increased reliability. If one fails, automatically the other one will pick up the function. Okay, and in that we have the high upfront cost because we need to be ready with the two systems, right? The other one is single generator plus load shedding, which includes facilities to reduce the cost by a single generator and automatically shedding lower priority loads during an outage to stay within the capacity. Okay, if the capacity is less, it will automatically load shed during the generator operation itself. Okay, and it has comparatively lower initial investments we have. Okay. Then mobile units still need always on power. Okay, mobile units always, in different biomedical purposes itself, like if doctors or if someone is going for camping and all, they should have the units with power, right? So these type of uninterrupted power which we need for the equipment's use, So it includes steady voltage and grounding, UPS for seamless transmissions and secure data links. Okay, secure data links. All these three should be there for every mobile units. Now, the invisible pulse, how SCADA powers the energy grid. So SCADA, as we know, it is a platform which monitors, okay, and it is the energy nervous system. It is supervised, monitor thousands of field devices in real time at a time. Okay, and acquire, collect raw data from sensors across the grid, then control. It issues the commands to actuators and equipment remotely. That means I can control from the system to peripheral devices. That means actuators. Actuators in the sense, if you are having a control valve, okay, the control valve will be working. That means if it is an electronic control valve or if it is a pneumatic control valve, there will be some actuator, right? So if it is an electronic control valve, there will be some sort of box you might have seen, which is nothing but an actuator. If I'm giving some sort of signals to it, it will it will open or close the valves, right? So you might have studied about the basic current range and all, 4 to 20 milliamps. And the pressure is like 3 to 15 psi. So this is a control system actuator where I can give signals from SCADA systems. Okay. So layer 0, the sensors, how the sensors will happen in the area where the ambience has to be measured, where the parameters has to be measured. Sensors and transducers, it capture voltage, current, pressure, flow, etc. Then intelligent devices, it relays or smart meters provides deep diagnostics on equipment health. It will provide us the correct information when it has been serviced or when the schedule will be, and if any error occurs, this shows error. That message will be displayed by intelligent electronic devices. So layer 1 is nothing but the brain. Raw sensor, data is meaningless without processing. Remote terminal units and programmable logic controls aggregate, interpret, and act on field signals in real time. So field sensors we have, RTU or PLCs we have, then digital packets. Okay, so all these things are, we can call it as the brain of SCADA. Then the communication highway. As normally we said, initially it was just like a rack. Now the rack will be communicated to the SCADA through different protocols, TCP/IP, transmission control protocol, internet protocol. It uses different sort of protocols. It connects to the PLCs and systems. And somewhere we can use fiber optic cables as well for much more inputs. If I'm having a lot of inputs, we go for fiber optic systems. Okay. Then wireless links for remote or erect terrain for cabling is impractical, where I'm using radio and microwaves as well. Then, of course, the layer 3 is nothing but the control room, where operators can see live visual map and the entire energy systems from individual breakers to regional load flows. So all these things coming under our, from the control room. Then the actuation loop. Actuation loop, in a sense, when a SCADA system works, it is just like not observing, it acts. Like when conditions exceed the safe limit, the system closes the loop automatically without waiting for human intervention. So that means detect, then it goes to decision, then it goes to transmission, then it goes to actuation without any human intervention. That means I'm having an error, it will detect, it will decide what to do, then it will transmit the signal to the actuator, then actuator will actuate and it will, the process will shut down if required. So necessary action will be taken place. The actuation loop. So from analog to action, the SCADA handles 4 fundamental data types, which is status, analog, set point, and accumulator. Status, in essence, binary states, monitoring breakers, switches, and alarms. The next is analog, continuous values, tracking power flow, voltage levels, and frequency. And set point, we have some target values. I'll give you a real-time example, then you will be easy to understand how it functions. Then it goes to accumulator, cumulative totals, managing every metering and consumption data over time. Okay. Now I'm taking you to an industry where the pharma, how the pharma company works, how the HVAC system works along with the PLC and SCADA. So this is the main unit where this we can call it as AHU, air handling unit. Okay, air handling unit. AHU controls temperature, pressure, and humidity. Temperature, pressure, and humidity of a room. Now I'll tell you one example. So if I'm having a fever, I'll go to doctor, I'll get prescribed the medicine like capsules or something. If I'm opening that capsule and keeping on my hand, it will get sticky within 30 seconds or 1 minute, right? Because of humidity, as you know. So now you just think, where I'm manufacturing this capsule? In a room, of course. And if it is getting sticky over that time itself, of course, before packing, then the entire batch, the entire tablet will be damaged and we cannot use it, right? So when I'm going to the air handling unit, what it does, here we have a blower motor. In the figure, you can see a blower motor. Okay, this is the supply fan section. Now I'll just take an example of medicine, salbutamol tablet, small tablet we have, right? Salbutamol for wheezing purpose and all we normally use, right? So that medicine, if manufacturing in a room, and the powder, that is just like powder, right? Powder will be formed like a small tablet. So I'm just pressing it with some sort of moisture and it is getting pressed in the form of tablet, correct? If the powder is spread all over the room and if powder is going out of the room to the corridor, what will happen? There are a lot of humans, right? So if it goes to the corridor, everyone will inhale that particular tablet powder. So what we can do from our engineering side, we have to reduce the pressure inside the room and increase the pressure outside the room. We know normal atmospheric temperature is 1, right? 1 atmosphere. So 1 atmosphere, I'm just reducing into 0.9 inside the room. And I'm keeping 1.1 at the corridor. Then now what will happen? The powder inside will not go from inside from the cubicle to outside. How I will make with this AHU? I can tell you, this is our supply fan section. Supply fan section includes, okay, which will take air, and it goes to the chamber, correct? It goes to the chamber. This is the supply duct, supply air. It goes to room. If I'm reducing the supply air to the room, and you can see at the left-hand side, the return air, which comes from the room. I'm increasing the return air speed by using a blower motor. This is the blower motor. I will reduce this return air. And I will increase the return air and reduce the supply air. What will happen? The pressure will go down inside the room, correct? And in the corridor, I'll just do opposite. So the blower motor functions. Actually, what it does, the air will come through pre-filter. Pre-filter means HEPA filter. Okay, high efficiency particulate air filter, HEPA filter we are using for it. So that HEPA filter, through the HEPA filter, the air will come and it goes through, it touches the cooling coil, it touches the heating coil, then it goes to the room. This is what happens. Why it touches cooling coil and heating coil, I am going to say now. Now I need a temperature limit of 30 degrees Celsius in the room. What I will do? Through the heating coil, I will supply hot water from the utility. So when the air comes and it touches the heating coil and it comes out, automatically the air temperature will go high. It will be supplied to the room. So the room temperature will go high. We will be measuring it with the temperature sensor. Now, I wanted to bring the temperature down. What I will do? I will close the heating coil and I will start the cooling water flow in the cooling coil. So what will happen? The air will touch the cooling coil. Cooling coil, in essence, you can see the in vehicles and all, we have some types of radiators, right? Minute coils. So such type of coils will be there inside the AHU. So when it touches the small coil, cooling coil, the temperature goes down. Opening and closing of this cooling coil and heating coil supply which will be controlled from the PLC panel based on the sensor signal processing which comes from the room. The room we have sensor, it will directly take into the processor, PLC. PLC will just check with the set point whether it is matching. If it is low, what it has to be done? That signal will go to the actuator of the respective coils. So in this way, I can control the temperature of the room. Pressure I already said. I will control the damper, air damper to the control the air damper through actuation only. That actuator will work based on the system. Now humidity. How I will control the humidity? We told about the parameters, right? Temperature, pressure, you might be understood. So how we can control the humidity? We control cooling coil and heating coil in a percentage to control the humidity. Both the cooling coil and heating coil will be operated to control the humidity of the room. You know what it happens, why we are doing all these things? This will be monitored in the BMS system, building management system. In that building management system, we have a graph. 0 line will be there, then high and very high line will be there, low and very low will be there. So if temperature is crossing high, it will give an alarm to us. It will give an alarm to us. By the same time, I have to go and check whether the system is perfect or not, the sensor is perfect or not. If sensor is faulty, I have to replace. Otherwise, I have to inform the respective section to stop the manufacturing. But it is not practical. If I am stopping the manufacturing, of course, in a company, the losses will be in lakhs. So we have to act quickly. So BMS system, what it does, when it goes to low or high or low, it will automatically give alarm. It will show us where the fault is. Then I can directly go and check and correct or rectify the fault, what it happens. So this is the thing which happens in the form of. And if the graph is going above the very high or above, coming very low, below that very low condition, the entire medicine batch will be rejected. It will not go to the market. It will be, it will not be approved by the QA of the company. And we have to write the engineering explanation why it has happened. We have to rectify all these things. So now I wanted to share how the blower motor, now I told that supply air can be increased or return air can be decreased. How we will do all these things? By using blower motor speed. Blower motor speed means it runs in a particular speed. How I will control the speed? By using VFDs. Now we are coming into the picture. Variable frequency drives. Okay, variable frequency drives. So variable frequency drives includes, if it is a 1 kilowatt VFD, I can control 1 kilowatt motor. If it is 1 kilowatt VFD, I can control 2.5 kilowatt motors. So the total load should be equal to the spec. Total load should be the spec. So that is what here. Now, how I will control this? Okay, how I will control the VFD panel? Okay, when we are making it on, when we are making the control on, okay, I can reduce or increase the frequency. How the frequency gets increased or reduced? And what is the importance or what is the value I will get? How I will reduce the frequency in a VFD? I can just show you that. You might have heard IGBTs, right? IGBT. This is the same thing where in the VFD, what I have done, I am just focusing into the IGBT session. IGBT session includes the firing angle of IGBT. We already studied all these things, right? In a theoretical manner. By adjusting the firing angle of IGBT, I can reduce the frequency or increase the frequency. Reduce the firing angle in the sense switching on the IGBTs, switching on and off the IGBT. So you might be studied about the IGBT characteristics, switch on off characteristics. I don't want to explain it, but still, if I'm having that firing angle, I can make it on and off. And based on this, I can control the speed of blower motor. So in this, blower motor will be controlled. So now one more thing I can say here as a project. Okay. For energy saving, if it is an RYB connected motor, RYB connected, I mean three-phase motor, I'm connecting it through a VFD. Normally it runs in 50 Hertz as we know. Okay, it is apart from this, okay, apart from this. So I'm reducing the frequency into 45. I'm reducing the frequency into 45. What will happen? Of course, the current through the phase to the phase will be reduced. If the current reduced, the efficiency, I mean, the power output normally gets reduced and the consumption of energy will be reduced. But as we know, in our ceiling fan, if it is a 50 hertz, it is operating in 50 hertz, right? I'm reducing the speed between 4 and 5. In a regulator, you can see 4, 5, right? So I'm just reducing between 4 and 5. Is there any much difference in that? No. We cannot feel it somehow. So very small change in the frequency can save more current and more power, more energy in the system. It can connect to the consumption bill, electricity bill. So the energy saving can also be done by using VFD. And you know, I'll tell you an exact practical example because I have done all these things. What I've done is I implemented a VFD for a RYB motor and I got the return in 4 months. Normally, when I'm giving a proposal to the firm, whether they will check in 6 months whether I'll get the payback or not. If payback within 6 months, of course, it will be approved. Around 3.5, 4 months, I got the payment of the VFD from the energy bill. You can calculate. Because just imagine, I can say you an example with this. 11, 12, 13 are the respective amperes of RYB phases. If I'm connecting VFD, it will be reduced to 8, 9, 10. Now you can calculate the power as per equation. So that will be, or that can be done as part of energy saving. That can also be done by using IGBTs. So all these things coming under our PLC, SCADA and DCS systems. Okay. Now I already said SCADA will be monitored and DCS will be giving a confined plant environment and which will be using or which will be controlling the entire plant from a particular center. Okay, we're using a particular center. So coming to the conclusion, which we are coming to, reliability and resilience. So what we have learned today. What is smart grid? What is the importance of smart grid? And what is the reliability? And what is resilience? And what are the research points in resilience pending? Pending in the sense, I have just noted only 5 to 6 points. You can get enough more points as per your this one. No issues in that. I just shared the paper as well. So from that point, a paper itself, I've got that much research gaps in the case of resilience itself. Okay. Then we come to the security of the system, how we can do the secure connections and real-time implication in biopharma applications. How we can implement a VFD, what is the importance of VFD implementation in a AHU, HVAC system and BMS, etc. So coming into the conclusion, and thank you for the time and you can ask the questions if any. I'm open to work.
Any queries from the
Participants,
participant side?
Yeah.
So I think there are no queries. Shall I wind up, sir?
Yeah, please. Thank you.
Thank you, sir, for such an insightful and engaging session. Your valuable expertise, practical insights, and clear explanation have truly enriched our understanding of the topic. We sincerely appreciate the time and effort you have taken to share your knowledge with us. On behalf of the Department of Electrical and Electronics, I extend a heartfelt gratitude to you. Thank you once again, sir, for being with us today. We look forward to interacting with you again in the future, sir. Once again, thank you.
Thank you. Thank you all.
Participants complete the feedback form before leaving the meeting.